On the night of July 15, 1977, something unusual happened. Jerry R. Eman, a professor at Ohio State University, was helping search for signs of life beyond Earth. He was monitoring radio signals when he noticed something unusual. The computer recorded a strong signal that lasted 72 seconds coming from the direction of the constellation Sagittarius. The signal was about 30 times stronger than the usual background noise. When the computer printed it out, it showed a sequence of letters and numbers 6EQJ5. Jerry was so surprised that he wrote the word "wow" in the margin of the paper. That's why it's now known as the wow signal. It seemed like the source of the signal was moving in a pattern, like the light from a lighthouse sweeping across the ocean. We caught the signal for just a moment when it was pointed right at us, and then it was gone. Even today, scientists wonder where it came from and what it might mean. The wow signal was detected using a huge telescope called Big Air at Ohio State University. It was built to search for extraterrestrial intelligence. The telescope was about the size of 3 football fields, with mirrors that captured signals and sent them to 2 receivers for processing. But Big Air had a problem. After it found the wow signal, there was a delay before it could check the same spot in space again. By the time it looked back, the signal was gone. This made it hard to confirm where the signal came from. Unlike today's telescopes, Big Air couldn't move freely. It could only tilt up and down, so it was limited to watching a narrow strip of the sky. The engineers came up with a clever idea that allowed telescopes to look up to the vast sky. They used the Earth's rotation to move the telescope left and right, allowing it to cover more of the sky over time. Even with its limitations, Big Ear was a valuable tool in the search for signals from other worlds. It gave us a brief glimpse of something truly mysterious, leaving us to wonder if we might have missed more signals from the same spot. This brings up a key point about how organizations like search for extraterrestrial intelligence life in the universe. Space is incredibly vast, and their resources are limited. Instead of focusing on one area for a long time, they have to make smart decisions about how to use their equipment. They can't spend years looking at one part of the sky, hoping for a reply. So they take a different approach, which is moving their telescopes across large areas of space to cover as much ground as possible. This is like casting a wide net in different places rather than staying in one spot and waiting. By scanning different areas, they increase the chances of picking up signals, even if it's just for a moment. It's a practical choice, given how uncertain we are about where or when a signal from intelligent life might show up. Comparing this to fishing can help explain it, but it's not exactly the same. Alien signals, if they exist, aren't like fish that can be drawn in by what we do. They aren't influenced by our efforts to find them. Even though moving the telescope around might seem random, it's the best way to search the vastness of space since we have no idea where or when a signal might appear. But this approach has its challenges, especially when it comes to following up. Over the years, telescopes like Big Air have detected several odd signals like the wow signal that we don't fully understand. Without the ability to focus on these signals long enough, they remain unexplained. This means we miss out on valuable data, and it becomes hard to understand where they came from or what they mean. So, what does this all mean? One reason we might not have found intelligent life yet could be because of how we search for it. Of course, this is just one explanation among many. But there are also a lot of theories about our place in the universe and the nature of other civilizations. These ideas give us much to think about. If you're interested, stay tuned for another video where I'll explore these theories in more detail, giving a closer look at the possibilities of life beyond Earth. The question of whether aliens are out there watching us is both exciting and complicated. With the billions of stars and galaxies in the universe, the chances of life existing beyond Earth seem possible. If even a tiny fraction of planets around those stars could support life, then life could be more common in the universe than we think. There are many reasons why we haven't made contact with aliens yet. One reason could be the huge distances between stars, making it hard to communicate or travel across space. Another possibility is that civilizations might rise and fall at different times, meaning they could miss the chance to meet each other. One interesting thing to think about is how advanced civilizations might communicate. They could be using methods we don't understand yet. It's also possible that these civilizations choose not to contact us directly. They may be watching us like we study animals that are less advanced. The WOW signal, discovered in 1977, shows how exciting and difficult it is to search for life beyond Earth. Even though scientists have tried hard, we haven't detected that signal again. It's still a mystery, reminding us how much we have to learn about the universe and our place in it. At the heart of our search for life is a big question. Are we alone? Whether or not we find out in our lifetime, the search helps us grow and learn more about the world around us. If we ever do make contact, it would be a huge moment in human history. But what would happen next? How would it change the way we live, what we value, and how we see ourselves? Would we even be ready for such a discovery? Search for Extraterrestrial Intelligence, the organization leading this search, is hoping to find a clear signal from space that happens more than once, just like the WOW signal. To know for sure that we're not alone, we'd need to see the same signal again. To actually talk to aliens, we would need to either send them a message and get a reply, or they'd need to contact us first. We could send spaceships or robotic probes, but space travel is very slow with the technology we have now. For example, Voyager 2, a spacecraft launched in 1977, took almost 49 years just to leave our solar system. To reach the nearest star, which is 4 light-years away, it would take over 81,000 years. That's longer than 2,700 generations of humans. So, unless aliens live really close, reaching them would be very hard. Even if we get better at building spaceships, traveling at the speed of light is nearly impossible. It would need more energy than we could ever gather. But some scientists are thinking about different ideas, like wormholes. These could let us move faster than light by moving space itself. This might be a way to travel without breaking the laws of physics. For now, sending messages through space is much easier and cheaper than sending ships. It's like making a phone call instead of going to someone's house. Most likely, if we ever talk to aliens, it will start by us picking up one of their signals. Even though the speed of light is super fast, about 300 million meters per second, there's still a delay in communication. If we sent a message to an alien civilization far away, it would take time to get there, and then more time for their response to come back to us. We've only been using radio technology for about 120 years. This means we could only exchange messages with aliens that live within about 60 light-years from Earth. 60 years for our message to get to them, and 60 years for their reply. Our moon is one of the biggest objects in our solar system, almost as big as Mercury. This proposes a big question. How did Earth and the moon form like this? Why do these two bodies orbit each other? There are some interesting points about the Earth and the moon system. For example, a space probe orbiting Mars took a picture that shows Earth and the moon from Mars' perspective. It's a beautiful reminder of how connected these two are. One cool thing about the moon is that it has very little iron in its core, while Earth has a lot of iron. This iron in Earth's core helps create its magnetic field. So, why does Earth have so much iron, but the moon has so little? It's confusing because if the moon and Earth formed in the same area, you'd think they'd have similar amounts of iron. Another curious thing is how much spin there is in the Earth-Moon system. The moon is quite large compared to Earth. It orbits Earth quickly, and both the moon and Earth spin. In physics, we know that spin doesn't just appear out of nowhere. It has to come from somewhere. So why are the Earth and moon spinning so fast, and why is the moon orbiting Earth so quickly? One of the greatest moments in history was when humans landed on the moon in 1969. We brought back moon rocks and found that they are very similar to rocks on Earth. This suggests that the Earth and the moon may have come from the same source. By studying the decay of certain elements in the moon rocks, scientists figured out that the moon is about 30 to 50 million years younger than Earth. While this might not seem like a huge difference, it still tells us that the Moon formed a little after the Earth. Another interesting fact is about isotopes. Isotopes are different forms of the same element. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. The same idea applies to oxygen. The ratio of different forms of oxygen can be measured very accurately. Across the solar system, these ratios are different depending on where a planet formed. But on Earth and the Moon, these ratios are almost the same, meaning they likely came from the same place. So here's the question. The Moon is a little younger than Earth, spins quickly, has similar materials to Earth, but has very little iron. What could explain all this? There is a popular theory that makes sense based on the evidence, though some scientists still have questions about it. This theory is called the giant impact hypothesis. It suggests that about 50 million years after Earth formed, a planet about the size of Mars came very close to Earth. It collided with Earth, knocking off a lot of debris, but it didn't hit Earth's core. When planets form, heavier elements like iron sink to the center. So when the collision happened, the material that got knocked off had very little iron, because most of Earth's iron was already in its core. The collision that formed the Moon also caused a lot of spin, kind of like kicking a football on the side to make it spin and curve. This explains why the Earth and Moon have so much spin today. The Moon was made from the debris of this collision, which is why it has similar materials and isotopes as Earth. Since the collision happened about 50 million years after Earth formed, it also explains why the Moon's rocks are a bit younger than Earth's. It seems the Moon formed from this giant collision around 4.5 billion years ago. The evidence backs this up, from the samples we brought back from the Moon to the 4 main observations about how Earth and the Moon are related. But that's not all. This collision didn't just make the Moon, it also had a big effect on Earth. It likely tilted Earth's axis, which is why we have seasons. Without this tilt, Earth's climate would be very different, and it might not support as much life as it does now. The Moon also helps keep Earth's rotation steady, stopping it from wobbling too much, which could have caused big changes to our environment. The gravitational pull between the Earth and the Moon also creates tides, which have shaped life on Earth for millions of years. The regular rise and fall of ocean levels have been important for coastal life and even human activity over time. Interestingly, the Moon is slowly moving away from Earth. Each year, the Moon drifts about 3.8 centimeters farther. This affects the Earth's rotation, making our days longer. Millions of years ago, days were shorter, but as the Moon continues to drift, our days will get a bit longer over time. The giant impact hypothesis is the most widely accepted idea about how the Moon formed, but there are other ideas too. One is the fission theory, which says that the Moon was once part of Earth, but separated because Earth was spinning very fast in its early days. But this theory has trouble explaining the Moon's current orbit and how such a separation could have happened. Another idea is the capture theory. It suggests that the Moon formed somewhere else in the solar system and was later captured by Earth's gravity. This could explain why the Moon is a bit different from Earth in some ways, but capturing something as big as the Moon without it breaking apart or escaping again seems unlikely. Even though the giant impact hypothesis is the most accepted, scientists are still studying and debating exactly how the Moon formed. The special connection between Earth and the Moon has had a big impact on life here. The Moon's gravitational pull causes tides, which have helped shape the evolution of life and human civilizations. The regular rising and falling of the oceans have affected coastal areas and human activities for thousands of years. The Earth-Moon system is one of the most discussed topics in cosmology, offering clues about how planets and moons form. The differences in their makeup, their shared spin, and the ongoing relationship between Earth and its only natural satellite all tell an amazing story about our place in the universe. While the giant impact hypothesis is the most popular theory about how the Moon was formed, there are some other interesting ideas that scientists have considered. One early idea is called the fission theory. This theory suggests that the Moon was once part of Earth, but separated when Earth was spinning very fast in its early days. Imagine the Earth spinning so quickly that a chunk of it broke off and became the Moon. It's like when you spin something really fast and small bits fly off. The main issue with this theory is that it doesn't fully explain how the Moon ended up in its current orbit. Plus, Earth would have needed to be spinning way faster than we think it ever did. So, while this idea is interesting, it has some defects. Another idea is the capture theory. According to this theory, the Moon didn't form near Earth at all. Instead, it formed somewhere else in the solar system and was later caught by Earth's gravity. The Moon, in this case, would have been a wandering body that passed close to Earth and got stuck in orbit around it. The problem with this theory is that capturing such a large object like the Moon without it breaking apart or escaping again is very difficult. For this to happen, there would need to be very specific conditions that are hard to explain with what we know about space. Another theory is the code formation theory. It suggests that the Earth and the Moon formed together at the same time from the same cloud of gas and dust that was orbiting the Sun. In this idea, as the material came together to form the Earth, some of it also formed the Moon right next to it. While this theory helps explain why the Earth and the Moon have similar materials, it doesn't explain why the Moon has much less iron than Earth. If both formed in the same area, you expect them to have more similarities in their composition. Another idea, called the multiple impact theory, suggests that the Moon was formed by not just one big impact, but by several smaller impacts over time. Instead of one planet-sized object hitting Earth, many smaller ones may have collided with Earth, creating debris that eventually came together to form the Moon. This theory explains why the Moon might be made of different materials, but it's not as widely accepted because it's harder to find solid evidence for multiple impacts. One of the most famous features in our solar system is the Great Red Spot on Jupiter. This huge storm, larger than Earth, has been active for at least 400 years, and maybe even longer. The Great Red Spot is a massive swirling storm that has caught the attention of scientists ever since it was first seen. But what exactly is this storm, and why has it lasted for so long? The Great Red Spot is a high-pressure area in Jupiter's atmosphere, creating a storm that spins counterclockwise in the planet's southern hemisphere. The storm is so big that it can be seen from Earth through telescopes. In fact, it's about 1.3 times the size of Earth. The edges of the storm spin faster than the center. One of the biggest questions about the Great Red Spot is its reddish color. Scientists aren't entirely sure why it's red. Some ideas suggest that chemicals in Jupiter's atmosphere, like phosphorus or sulfur, might be causing the color when they react to sunlight. Another idea is that chemicals from deeper in the storm might be getting pushed to the surface. Whatever the reason, the red color makes the storm stand out among Jupiter's bands of white, brown, and yellow. Another fact is that the Great Red Spot has lasted for so long. On Earth, storms usually only last a few days or weeks, but the Great Red Spot has been around for centuries. This is partly because of Jupiter's unique atmosphere. Jupiter is a gas giant, meaning it doesn't have a solid surface like Earth. Since there's no land to slow it down, the storm can keep going. Also, Jupiter's large size and fast spinning help the storm stay active. Jupiter's quick rotation plays a big part in keeping the Great Red Spot going. Jupiter spins much faster than Earth, completing one full turn in just under 10 hours. This fast spinning creates strong winds, called jet streams, that help hold the storm in place. These winds act like walls, keeping the storm in its area and stopping it from fading away. The way these winds interact with the storm helps keep it going strong. Even though the Great Red Spot has been around for a long time, it won't last forever. Over the past few decades, scientists have noticed that the storm is slowly shrinking. Back in the 1800s, the storm was about 25,000 miles wide. Now it's less than half that size. Scientists are studying this change to understand why it's happening and what it might mean for the storm's future. The exact reasons for the shrinkage aren't fully known yet, but it could have to do with changes in Jupiter's atmosphere or interactions with other storms. The wind inside the Great Red Spot is incredibly strong, reaching speeds of up to 400 miles per hour. These winds create tall clouds that rise high above the surrounding atmosphere. The storm on Jupiter, known as the Great Red Spot, has a layered structure with different temperatures and wind speeds at different heights. These layers help scientists learn more about how the storm works and how it affects Jupiter's atmosphere. The top of the Great Red Spot is much cooler than the clouds around it, which shows that the storm goes deep into Jupiter's atmosphere. In recent years, NASA's Juno spacecraft has given us a closer look at the Great Red Spot. Juno, which has been orbiting Jupiter since 2016, is packed with tools to study the planet's atmosphere, magnetic field, and inner structure. Juno's close passes over the Great Red Spot have revealed that the storm reaches much deeper into Jupiter's atmosphere than we thought, possibly hundreds of miles deep. This shows that the Great Red Spot is a massive structure with strong roots deep inside Jupiter's thick atmosphere. The Great Red Spot also helps us understand atmospheres on other planets, even ones outside our solar system, called exoplanets. By studying this giant storm, scientists can create models to predict weather on other gas giants and even potentially habitable planets. This information helps us learn more about how atmospheres work not just in our solar system but across the universe. The Great Red Spot is a mystery that continues to inspire us. It reminds us of the powerful forces at work in our solar system. Every new discovery about the storm helps us get closer to understanding it, but also shows how much more there is to learn about Jupiter and other giant planets. This storm has lasted for centuries and continues to change, making it a perfect place to study how atmospheres behave under extreme conditions. Beyond science, the Great Red Spot has become a cultural symbol. It has appeared in many works of science fiction, art, and literature, representing the unknown wonders of our solar system. Its striking appearance makes it a favorite subject for both professional astronomers and amateur stargazers. Looking at the Great Red Spot through a telescope is a thrilling way to connect with the vast universe beyond Earth. Studying the Great Red Spot also helps us appreciate the balance of Earth's atmosphere. While Earth's storms are much smaller and don't last nearly as long, they work in a similar way. The future of the Great Red Spot is uncertain. Will it keep shrinking until it disappears, or will it find a way to stick around for many more centuries? Scientists are eager to know, and missions like Juno will help answer these questions. The information gathered by Juno and other future missions will help scientists make better models of Jupiter's atmosphere and understand how its most famous storm will behave in the years to come. This photo, taken by a telescope in 1917, shows a blurry image of Mars with dark patches. Back then, some respected astronomers thought these markings might be signs of plants. But that idea was proven wrong when spacecraft started visiting Mars. The first was Mariner 4 in 1965, which sent back grainy images of the surface. Even President Lyndon Johnson reflected on how life as we know it might be more unique than we thought. Today, many spacecraft have visited Mars, and we now see a world full of geological wonders. Mars has giant canyons, like the Moreno Valley, which stretches halfway across the planet. To put it in perspective, the Grand Canyon on Earth would fit inside one of its smaller side valleys. Mars also has massive volcanoes and signs of ancient lakes and oceans. Right now, the Curiosity rover is exploring a dry lake bed and has found signs of organic molecules and minerals that only form in water. We now know that about 3 to 3.5 billion years ago, Mars was much like Earth. It had rivers, oceans, and seas. It might have even been a place where life could have started, but we don't know for sure if that happened. This completely changes how we think of Mars. A planet with water has everything needed to support life. Even if there weren't Martians back then, and even if there aren't any now, there might be in the future. Because those Martians could be us. One of the biggest mysteries is what happened to all its water. Billions of years ago, Mars had flowing rivers and maybe even big oceans. Today, though, it's a cold, dry desert with only small amounts of water in its atmosphere and ice at its poles. So, what caused this huge change? To figure that out, we have to look at Mars' past. Geological features like river valleys, dry lake beds, and mineral deposits tell us that Mars once had a thick atmosphere. This thick atmosphere would have kept Mars warm enough for liquid water to exist. But over billions of years, Mars lost most of its atmosphere, leaving it cold and dry. One of the main reasons for this loss is the solar wind. The solar wind is a stream of charged particles coming from the Sun. Unlike Earth, Mars doesn't have a global magnetic field to protect its atmosphere from these particles. Earth's magnetic field acts like a shield, deflecting the solar wind and keeping our atmosphere safe. But Mars doesn't have this protection. Over time, the solar wind stripped away Mars' atmosphere. This process, called atmospheric sputtering, involves solar wind particles hitting the atmosphere and knocking its molecules into space. As Mars lost its atmosphere, the planet couldn't hold on to heat. With lower pressure and colder temperatures, any remaining liquid water either froze or turned into gas in a process called sublimation, where a solid turns directly into gas. This likely contributed to the disappearance of water on Mars' surface. Mars' weaker gravity also played a big role in this. Mars has only 38% of Earth's gravity, which means it can't hold onto its atmosphere as well as Earth can. Over time, lighter molecules like hydrogen and oxygen, which are needed to make water, escape into space. This gradual escape made it even harder for Mars to keep its water. Mars, long ago, was much more active with volcanoes than it is today. In its early years, Mars had massive volcanic eruptions that released a lot of gases into the atmosphere. These gases helped keep the planet warm through the greenhouse effect, allowing liquid water to exist. But as the volcanic activity slowed down, the atmosphere wasn't replenished. This caused the atmosphere to get thinner, which made the planet colder and drier. Even though much of its atmosphere and water are gone, Mars still holds a lot of water as ice. Recent discoveries by rovers and orbiters have found large amounts of water ice just beneath the surface, especially near the poles. Radar data from the Mars Reconnaissance Orbiter shows that there are huge underground ice sheets, which could hold more water than all of Earth's Great Lakes combined. Some scientists also think there could be liquid water hidden in lakes beneath the surface, covered by ice and soil. These water sources offer a glimpse into Mars' wet past and give hope for future exploration. Mars' iron core plays a big part in its current conditions. Unlike Earth, which has a molten core that generates a strong magnetic field, Mars' core is mostly solid. This weak magnetic field left Mars exposed to the solar wind, a stream of charged particles from the Sun. Over billions of years, these particles stripped away much of Mars' atmosphere, leading to the loss of surface water. Without a strong magnetic field, Mars couldn't keep the atmosphere needed to support liquid water. Understanding what happened to Mars' water is important not just for science, but also for future human exploration. Water is essential for life and will be critical for astronauts on Mars. It can be used for drinking, growing food, and making fuel. By figuring out how Mars lost its water, we can better plan for future human missions. If we can find and use the water hidden under Mars' surface, it will make long-term human missions more possible. Mars gives us a chance to study how planetary atmospheres evolve. By comparing Mars to Earth and other planets, scientists can create better models to predict our own planet's future climate and explore the potential for life on other worlds. In recent years, missions like NASA's Perseverance rover and the European Space Agency's ExoMars mission have focused on searching for signs of past life on Mars. These missions are studying the planet's geology and looking for markers that might indicate life once existed there. Water is key to these investigations, as it's essential for life as we know it. By understanding where water once existed on Mars and how it interacted with the planet's surface, scientists can better judge the chances of ancient life on Mars. Mars' water story is a complex one, full of change and the processes that shape planets. While there are still many unanswered questions, Every new discovery helps us understand Mars a little more. The history of Mars' water, atmosphere, and climate keeps scientists and space enthusiasts fascinated, pushing us to keep exploring this nearby planet. This is a modern-day picture of Mars taken by a spacecraft. Everywhere we look, we see evidence of ancient rivers, showing that Mars was once a planet that could have supported life about 3 billion years ago. Mars is no longer just a mysterious red planet, it's a place full of potential and hope for the future. Saturn, the sixth planet from the Sun, is full of wonders and mysteries. One of its most fascinating features is the strange hexagonal storm that circles its north pole. This six-sided storm has caught the attention of scientists and space enthusiasts because it's something we haven't seen on any other planet. Let's take a closer look at this unusual storm. Unlike the round storms we're used to seeing on Earth, this storm has a clear hexagon shape, like a six-sided polygon. Each side of the hexagon is about 14,500 kilometers long, making it more than twice the size of Earth. The storm also has a powerful jet stream with winds that reach up to 320 kilometers per hour. What makes this storm even more interesting is how stable it is. The hexagon has stayed in place for decades, showing little change. While storms on Earth usually last for just days or weeks, this hexagon has been around for at least 40 years and possibly much longer. Scientists have come up with several ideas to explain how this hexagonal storm formed and why it's lasted so long. One of the main ideas is that the hexagon is caused by a standing wave in Saturn's atmosphere. On Earth, standing waves happen in oceans and the atmosphere, creating stable patterns that don't move with the flow of air or water. Similarly, the hexagon might be a standing wave created by Saturn's fast rotation and the heat coming from inside the planet. Saturn's atmosphere is mostly made up of hydrogen and helium, with small amounts of other gases like methane, ammonia, and water vapor. Saturn spins very quickly, completing one full rotation in just over 10 hours. This fast spinning creates strong winds and stormy weather patterns. The jet streams in Saturn's atmosphere may be interacting in a way that forms the stable hexagon. Another idea is that the hexagon comes from the way Saturn's atmosphere is layered. Each layer of the atmosphere has its own temperature and pressure, which can interact to form stable shapes like the hexagon. In experiments, scientists have even created hexagon-like patterns in rotating fluids, which suggests that this kind of pattern could naturally happen in Saturn's atmosphere. One of the most fascinating things about the hexagonal storm is its color. In photos taken by NASA's Cassini spacecraft, the hexagon changes color from blue to gold. These changes are likely because of the seasons on Saturn. During the winter, the hexagon appears blue, probably because certain gases condense without sunlight. As spring and summer arrive, the hexagon turns golden, likely due to sunlight triggering chemical reactions in the atmosphere. For the first 5 years of the Cassini mission at Saturn, scientists couldn't see the hexagon because it was winter at the North Pole, which lasts about 7 years. But in December 2009, spring came to the North Pole and the sun started to shine again. This allowed Cassini to take detailed images of the hexagon, revealing more details than ever before. Scientists at the University of Oxford have helped explain Saturn's hexagon by simulating how the planet's atmosphere interacts with a spitting jet stream. They found that by changing the speed of the jet stream and the atmosphere, they could create different shapes, including a hexagon. It turns out that Saturn's hexagon is formed by a powerful jet stream that mixes with the surrounding atmosphere. At the center of the hexagon is a massive, rotating storm that has been there for decades. In 2013 and 2017, NASA's Cassini spacecraft took close-up images of the hexagon. These images were used to make 2 videos, but a new mystery appeared. Why did the color of the hexagon change over those 4 years? The Cassini mission provided important data about Saturn's hexagon, revealing details we didn't know before. For example, Cassini found a giant storm in the middle of the hexagon that looks a lot like a hurricane, with a well-defined eye and strong winds. The storm is surrounded by clouds that are as tall as 100 kilometers above the rest of the clouds. The data also showed that the hexagon reaches deep into Saturn's atmosphere, which means it's not just a surface feature, but a complex structure that goes down many layers. Studying Saturn's hexagonal storm isn't just about solving one mystery. It also helps us understand how atmospheres work. This storm gives scientists clues about how fluids and gases behave under extreme conditions. These insights can improve weather models for both Earth and other planets. The long life of Saturn's hexagonal storm raises questions about how such patterns form and what keeps them going for so long. Studying this storm helps scientists learn more about the forces that drive weather on gas giants like Saturn and even planets outside our solar system. In recent years, scientists have used computer models to try and explain how the hexagon forms. These simulations show that rotating fluids can create stable hexagonal patterns under certain conditions. By changing the factors in these models like Saturn's rotation speed, its atmosphere's makeup, and the heat coming from inside the planet, researchers can better understand how the hexagon is created and stays in place. Saturn's hexagonal storm remains a topic of active research. Each new discovery helps us better understand this incredible feature and the forces that shape planetary atmospheres. Future missions to Saturn and other gas giants will likely provide even more data to unlock the secrets of the hexagon and other unusual phenomena. In conclusion, Saturn's hexagonal storm is a unique and puzzling feature in our solar system. Its geometric shape, large size, and ability to last for so long make it stand out. By studying the hexagon, scientists gain valuable insights into Saturn's atmosphere and learn more about how fluids and gases move on other planets. As we continue to explore our solar system, the hexagonal storm on Saturn remains a reminder of the complexity and beauty of the universe. One of the biggest mysteries in space is whether we are alone in the universe or even in our own solar system. Recently, we've found clues that life might exist on some of the moons of Jupiter and Saturn. We know that water is important for life, and astrobiologists, scientists who study the possibility of life beyond Earth, say that life also needs certain chemicals and a steady source of energy. For a long time, Earth was the only place we knew that had liquid water. But now we know that at least two other places have oceans. First, Jupiter's moon Europa, and second, Saturn's moon Enceladus. And there may be water in other places too. But what about the other ingredients for life? The icy moons Europa and Enceladus might have those as well. When NASA's Cassini spacecraft discovered water vapor and ice shooting out from Saturn's moon Enceladus, scientists were curious to learn more. Originally, Cassini was only supposed to fly by Enceladus 3 times, but it ended up making 23 flybys, gathering more information each time. What did they find? A salty ocean beneath Enceladus ice and strong evidence of hydrothermal vents. These vents, similar to the ones at the bottom of Earth's oceans, release chemicals that support small creatures like shrimp. If Enceladus has these vents, it could have the chemistry and energy needed for life. Imagine shrimp-like creatures living on another moon. On Jupiter's moon Europa, the Galileo mission provided clues that it also has a global ocean. NASA's Hubble Space Telescope later spotted what might be water plumes on Europa too. Now, NASA is building a spacecraft called Europa Clipper to study Europa and find out more. Both Europa and Enceladus have conditions similar to Earth's deep oceans, where life thrives around hydrothermal vents. On Earth, these vents support shrimp, crabs, and tiny microorganisms that don't need sunlight. Instead, they get energy from the chemicals in the vents, proving that life can survive in extreme conditions. Europa and Enceladus have thick ice crusts covering their oceans. Scientists think that beneath these icy shells, there could be warm, salty oceans that might support life. The ice acts as a shield, protecting the water from the harsh conditions in space. This makes these moons some of the best places to search for life beyond Earth. The discovery of plumes on Enceladus was a major breakthrough. These plumes shoot out from cracks in the moon's ice, called tiger stripes, and extend hundreds of kilometers into space. Cassini flew through these plumes and found water vapor, ice particles, and organic molecules. These organic molecules suggest that Enceladus has the building blocks needed for life. Findings of Cassini also revealed that the plumes coming from Enceladus contain salts and other minerals. This hints that there may be hydrothermal activity on the ocean floor of the moon. On Earth, hydrothermal vents are home to a wide variety of life, using the chemicals released by the vents to survive. If similar vents exist on Enceladus, it could mean that life could be hiding in its deep ocean. NASA is also planning a mission called Europa Clipper to explore Jupiter's moon Europa in greater detail. Scheduled to launch in October 2024, the Europa Clipper will study the ice and the ocean below. The spacecraft will look for signs of water vapor plumes and collect data that will help scientists figure out if Europa could support life. Europa's surface is covered with cracks and ridges, which suggests that its ice shell is moving and could be affected by the ocean underneath. The Galileo mission even found evidence of a magnetic field around Europa, which is thought to come from a salty ocean below the ice. This magnetic field is another clue that there is liquid water beneath Europa's surface. What makes Europa and Enceladus even more interesting is that they don't just have water and organic molecules. These moons also have energy sources that could support life. On Earth, life can survive in extreme places where the energy comes from chemicals, not sunlight. The hydrothermal vents on Europa and Enceladus might provide the same kind of energy that could sustain life. In addition to the Europa Clipper, other missions are in the works to explore these icy moons. One of these is the Enceladus Life Finder, a mission aimed at sampling and studying the plumes of Enceladus in more detail. By looking closely at what's in the plumes, scientists hope to find signs of life or at least conditions that might support life. The search for life on Europa and Enceladus is part of a larger effort to see if life could exist elsewhere in the solar system. These moons offer unique environments that could help us answer one of the biggest questions in science. Are we alone in the universe? If life is ever found on Europa or Enceladus, it would change the way we understand biology and suggest that life could exist in many different environments. Another interesting moon of Saturn is Titan. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers, though they're not made of water but of liquid methane and ethane. While this is very different from Earth, some scientists believe that life could exist in Titan's unique environment. Titan even has weather patterns, with rain and wind shaping its surface. NASA's Dragonfly mission is scheduled to explore Titan in 2028, searching for signs of life in its alien landscape. While Mars, Europa, Enceladus, and Titan are the most talked about candidates, there are other places in the solar system that might surprise us. For example, Neptune's moon Triton and Pluto, once classified as a planet, both have icy surfaces and might have underground oceans as well. The more we explore, the more we realize that life could be hiding in places we hadn't even considered. Even our neighbor planet Mars could host life. Mars is one of the first places scientists have looked for life. Long ago, Mars had flowing rivers, lakes, and possibly even oceans. Today, it's a cold and dry desert, but traces of water still exist in its ice caps and beneath the surface. Recent missions, like NASA's Perseverance rover, are exploring Mars, looking for signs of ancient life by studying rocks, soil, and the atmosphere. While we haven't found any direct evidence of life on Mars yet, the fact that it once had water gives us hope. It would also hint that the universe might be full of life, waiting to be discovered in places we've never even thought to look. The search for life beyond Earth has fascinated scientists for centuries. While Earth is the only planet where we know life exists, recent discoveries have proposed exciting possibilities that other places in our solar system might also support life. For life to exist, there are a few basic ingredients that are needed: water, the right chemicals, and a source of energy. Surprisingly, several moons and even some planets in our solar system meet these conditions, making them prime targets in the search for life. If we find life elsewhere in the solar system, it would be one of the most significant discoveries in human history. It would show that life can exist in a variety of environments and that Earth isn't the only special place in the universe. Even finding simple microbial life would be a breakthrough, as it would suggest that life might be common in the universe. Uranus, the seventh planet from the Sun, stands out for one very strange reason. It's tilted on its side. While most planets spin upright as they orbit the Sun, Uranus rolls around with its poles taking turns facing the Sun directly. This tilt is about 98 degrees, which is much more extreme than Earth's gentle tilt of about 23.5 degrees. To understand axial tilt, imagine a planet spinning like a top. The invisible line it spins around is called its axis. Most planets have their axis tilted slightly, meaning they don't spin perfectly upright. The angle between a planet's axis and its orbit around the Sun is its axial tilt. For example, Earth has a tilt of 23.5 degrees, which is why we have seasons. When one hemisphere of Earth is tilted toward the Sun, it experiences summer, while the opposite hemisphere, tilted away from the Sun, has winter. As Earth orbits the Sun, this tilt causes the seasons to change. However, some planets have very different tilts, and this can lead to some wild weather and unusual cycles. So, what caused this unusual tilt, and what does it mean for Uranus? Scientists think the reason for Uranus's tilt is a massive impact that happened billions of years ago, shortly after the planet formed. They believe that a giant object, possibly as large as Earth or even bigger, slammed into Uranus, knocking it over onto its side. This collision changed how Uranus rotated and set it on the unusual path we see today. Although this idea is widely accepted, we don't know the exact details of what hit Uranus or how it all happened. Some scientists have another idea that it wasn't just one big impact, but a series of smaller ones. They suggest that several smaller collisions over time could have gradually pushed Uranus into its current position. These smaller hits wouldn't have completely destroyed the planet, but they could still have tipped it over. Uranus's extreme tilt has a big effect on its seasons and climate. On Earth, we experience seasons because of our 23.5-degree tilt, but Uranus's 98-degree tilt creates much more extreme seasons. Each of Uranus's poles gets about 42 years of sunlight, followed by 42 years of darkness. This is because it takes Uranus 84 Earth years to go around the Sun once. So, for half of that time, one pole is bathed in constant sunlight, while the other is in complete darkness. This creates some of the most dramatic seasonal changes in our solar system. During its long summer, one side of Uranus stays in the Sun for years, while the other side is in the dark. Then, as Uranus continues its journey around the Sun, the situation reverses, with the other pole getting its long summer. The planet's atmosphere is also affected by this tilt. Uranus's atmosphere is mostly made up of hydrogen, helium, and methane. The methane is what gives Uranus its blue-green color, as it absorbs red light and reflects blue and green light. The planet also has incredibly strong winds, reaching up to 560 miles per hour, which, combined with the tilt, cause intense weather and storms. Another interesting feature of Uranus's atmosphere is the presence of dark spots, similar to the famous Great Red Spot on Jupiter. These dark spots are thought to be storms, and they can come and go over time. Scientists using telescopes, like the Hubble Space Telescope, have spotted these features and continue to study them to learn more about Uranus's wild weather. The unusual tilt of Uranus also affects its magnetic field. Unlike Earth, where the magnetic field is mostly in line with the planet's spin, Uranus's magnetic field is tilted about 59 degrees from its axis. This means the magnetic field is off-center and more complex. Scientists believe this strange magnetic field is caused by a layer inside Uranus made of water, ammonia, and methane, which act like a slushy mixture. The way this layer interacts with Uranus' rotation creates its unusual magnetic field. Studying Uranus's magnetic field helps scientists understand more about the planets inside. It is thought that Uranus has a core made of rock and metal, surrounded by icy materials. On the outside, there's a thick layer of hydrogen and helium gas, similar to Jupiter and Saturn. Learning about the magnetic field gives clues about Uranus's inner structure and how it formed. Along with its tilt and magnetic field, Uranus also has rings and moons that make it even more unique. The rings of Uranus were discovered in 1977, but they are different from Saturn's rings. They are darker, narrower, and made mostly of large particles. Scientists think the rings might have formed from shattered moons or captured objects, and they may not be very old. Uranus has 27 known moons, with the largest ones being Titania, Oberon, Umbriel, Ariel, and Miranda. These moons are named after characters from the works of William Shakespeare and Alexander Pope. Each moon has its own interesting features. For example, Miranda, the closest large moon to Uranus, has deep canyons and ridges that show it has been shaped by a lot of geological activity. This suggests a complex history of changes beneath the surface. Even though Uranus is a fascinating planet, it hasn't been explored as much as others. The only spacecraft to visit Uranus was Voyager 2, which flew by in 1986. It sent back some important data, but there's still much we don't know about this distant planet. Future missions could help us learn more about Uranus' atmosphere, magnetic field, rings, and moons, unlocking more of the planet's mysteries. There's also an idea that a large moon, or several moons, could have pulled Uranus over time, causing its tilt. However, the current moons of Uranus are small compared to the planet, so this idea is less likely than the giant impact theory. Understanding Uranus doesn't just help us learn about this one planet. It also teaches us about how planets form and change over time. Uranus is called an ice giant because it contains more icy materials compared to the gas giants Jupiter and Saturn. Studying ice giants like Uranus and Neptune helps scientists understand the variety of planets in our solar system and beyond. In recent years, more and more people are talking about sending a new mission to Uranus. This mission could include an orbiter and maybe even a probe to study Uranus' atmosphere up close. By observing the planet over a long time, scientists could learn more about its seasons, weather, and magnetic field changes. They could also study Uranus' rings and moons in more detail, giving us a clearer picture of this tilted giant. Another planet with an odd axial tilt is Venus. But Venus's tilt is strange for a different reason. Venus is tilted by about 177 degrees, which means that it's almost upside down. To make things even weirder, Venus rotates in the opposite direction to most other planets in the solar system. While Earth, Mars, and most planets spin counterclockwise, Venus spins clockwise. This backward spin is called retrograde rotation. So, what caused Venus to spin this way? One theory is that a massive object may have collided with Venus, flipping it upside down and changing its rotation direction. Another idea is that strong atmospheric forces, like winds and storms, may have gradually slowed down and reversed Venus's spin over time. Because of its slow and backward rotation, a day on Venus lasts 243 Earth days. But does an axial tilt matter? Axial tilts play a huge role in a planet's weather, seasons, and even life. On Earth, the 23.5-degree tilt creates our seasons and allows for the diversity of climates and ecosystems. Without this tilt, Earth would be a very different place, with fewer changes in weather and daylight throughout the year. On planets with extreme tilts, like Uranus, or no tilt at all, like Mercury, the day-night cycle and seasons are vastly different from what we're used to. Understanding axial tilts helps scientists learn more about how planets formed, how they evolve, and how they might support life. In 1950, during lunch with his colleagues, a famous physicist named Enrico Fermi asked, "If our galaxy is so huge, Where are all the advanced alien civilizations? This question is now known as the Fermi paradox. The paradox comes from the idea that, with around 400 billion stars in our galaxy, there should be many planets with intelligent life. If that's true, these civilizations would have had plenty of time to explore space and maybe even visit Earth. But so far, we haven't seen any clear signs that this has happened. To explain why we haven't found any aliens, even though it seems likely they exist, several ideas have been suggested. One theory is that traveling between stars might be incredibly expensive and require a lot of resources. For example, even sending a spaceship to the nearest star would take a huge amount of energy and money, making it almost impossible. Another idea is that even if a civilization starts exploring and colonizing other planets, it might be too hard to keep expanding across generations. The effort needed to move from one star system to another might be too difficult to maintain. Another possibility is that we live in a quiet part of the galaxy, where it's possible that the galaxy is full of activity in other areas, but we just happen to be in a quiet part where not much is happening. Another interesting theory is the zoo hypothesis. It suggests that Earth is like a zoo or nature reserve, where aliens are watching us from a distance, making sure we don't know they exist. To understand where the Fermi paradox comes from, we need to look at two important ideas. The first is the Drake equation, created by Frank Drake, a major figure in the search for alien life. This equation estimates the number of civilizations in our galaxy that might be able to communicate with us. The second idea is the Fermi paradox itself, which asks, why haven't we found any clear signs of intelligent aliens, like space travel or signals from other stars? Interestingly, the name Fermi paradox is a bit misleading. Even though it's named after Enrico Fermi, he didn't actually create this theory, but his question led to important discussions about alien life. The Fermi paradox has also influenced decisions about space research. For example, it led Senator William to stop funding NASA's Search for Extraterrestrial Intelligence program in 1981. Although Carl Sagan helped bring the program back briefly, it was shut down again in 1993 by Senator Richard Bryan. Despite the funding cuts, the search for alien life hasn't stopped. While NASA no longer funds search for extraterrestrial intelligence as it used to, research continues through other organizations. The Search for Extraterrestrial Intelligence Institute, a private non-profit organization, keeps looking for signs of extraterrestrial life. They work with universities, companies, and even government agencies, including NASA, to continue the search for aliens. Interestingly, the term Fermi paradox didn't come from Enrico Fermi himself. What we know about his thoughts comes from a lunch in 1950 at Los Alamos, remembered by physicist Eric Jones, who later interviewed Fermi's colleagues including Emil Konopinski, Edward Teller, and Herbert York. During this lunch, Fermi asked about space travel, which eventually led to what we now call the Fermi paradox. However, according to Teller and York, Fermi wasn't really focused on whether aliens exist. Instead, he was wondering if traveling between stars was even possible. This made sense in 1950, a time when rockets hadn't even reached orbit yet, let alone other planets or stars. The idea that no aliens on Earth means no aliens anywhere wasn't part of Fermi's original thinking. This idea was actually introduced by astronomer Michael Hart in 1975, not Fermi. Michael Hart argued that if intelligent aliens existed, they should have already colonized the Milky Way. Since we haven't seen any evidence of them on Earth, he suggested that humans might be the only intelligent beings in our galaxy. He even thought that searching for alien civilizations might be a waste of time and resources. However, many people disagree with Hart. They point out several possibilities including: first, space travel might be too difficult or impossible. Second, aliens might not be interested in colonizing other planets. And third, aliens might have visited Earth long before humans existed, leaving no trace. Even though Hart's idea has its critics, it's still widely discussed when we talk about the Fermi paradox. In 1980, physicist Frank Tipler built on Hart's ideas. Kepler considered the huge resources needed to explore the billions of stars in the galaxy. He suggested the idea of self-replicating robots with human-like intelligence. These robots could be sent to nearby stars, build copies of themselves using local materials, and then continue to spread across the galaxy. Kepler's conclusion was that since we haven't seen any of these advanced robots on Earth, it might mean we're the only intelligent civilization, not just in the Milky Way, but in the entire universe. This is a bold idea, but it's based on the simple fact that we haven't encountered any aliens yet. What we now call the Fermi paradox actually comes more from the ideas of Michael Hart and Frank Tipler than from Fermi's original question. Over time, these theories have been mixed together, causing some confusion about where the paradox came from. Fermi's original question was about space travel, not necessarily about aliens, but the ideas of Hart and Tipler have shaped the modern version of the Fermi paradox. The confusion around the Fermi paradox likely started in 1977 when physicist David Stephenson used the term in a publication, presenting Hart's theory as an answer to Fermi's original question. A more accurate name might be the Hart-Tipler argument against the existence of technological extraterrestrials. While this name isn't as catchy as the Fermi paradox, it better credits the real originators of the idea. Even though the Fermi paradox raises doubts, the search for alien life is still a major focus for scientists. The James Webb Space Telescope is giving us incredible new images and data, while Mars rovers are exploring the planet's surface up close. There are also plans for future missions to the farthest parts of our solar system. The question of whether we are alone in the universe remains unanswered. Until we find out, the search for extraterrestrial life will continue to be a top priority. How do we search for alien life? Scientists have come up with different ways to look for life beyond Earth. One important area is studying exoplanets. These are planets that orbit stars outside our solar system. The Kepler Space Telescope and other missions have discovered thousands of exoplanets. Some of these are in the habitable zone, which means they're at the right distance from their star for liquid water to exist. The habitable zone is crucial because liquid water is essential for life as we know it. Exoplanets in this zone are prime candidates for further study. For life to exist, it needs certain key ingredients. Besides liquid water, life requires elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements form the building blocks of organic molecules, which make up all known life forms. Interestingly, these elements are common throughout the universe. They've been found in interstellar clouds, comets, and even on other planets and moons in our solar system. Scientists are also looking for biosignatures, which are signs of life that can be detected from far away. For example, certain gases like oxygen or methane in a planet's atmosphere could indicate life processes. Another interesting area is the search for technosignatures, which are signs of advanced civilizations. This includes looking for radio signals, laser pulses, or other types of technology that might suggest intelligent life. While we search for life on distant planets, scientists are also exploring the possibility of life in our own solar system. Moons like Europa and Enceladus are especially exciting. These moons have oceans beneath their icy surfaces, which could have the right conditions for life, protected from space by thick layers of ice. As technology improves, our ability to search for alien life will keep getting better. New telescopes, space missions, and even artificial intelligence will increase our chances of finding and studying possible signs of life. The mystery of whether we are alone in the universe might one day be solved, thanks to these advances. The Fermi paradox points out a strange situation. We'd find ourselves in a universe that seems likely to be filled with intelligent life, yet none has made contact. Among the many theories born from this paradox, the zoo hypothesis stands out. Proposed by John Allen Ball in 1973, it suggests that alien civilizations are indeed out there, but they choose to stay hidden, much like caretakers of a wildlife reserve, quietly watching Earth from a distance. These advanced beings may remain hidden to avoid contaminating our world. Just as we are cautious about not spreading Earth's microbes to other planets, they could be equally concerned about introducing their own organisms into our delicate ecosystem. By maintaining their distance, they ensure that life on Earth continues to evolve naturally without external interference. They might be watching silently to preserve the balance, never revealing themselves so as not to disturb the natural course of our development. Another possibility is that communication between us and these beings may be far more difficult than we imagine. Their way of thinking, their perceptions of reality, might be so vastly different from ours that any attempt to interact could be confusing or even pointless. Perhaps for them, observing from afar is a more practical and peaceful option. They might prefer to study us in silence, avoiding any misunderstandings or disruption to our growth as a species. The idea of watchers also comes from this hypothesis that beings that observe Earth in a quiet, non-intrusive way. Their purpose may be scientific, or it may be to allow human civilization to develop independently, free from alien influence. Perhaps they see our world as too young, too unprepared for direct contact, and instead monitor us from the shadows, ensuring that we progress at our own pace. There's also the intriguing notion that the reason we've never detected alien contact might lie in the way we perceive time. What if these beings visit our planet, but only once every few thousand or even million years? Their visits could be so short that they leave behind no visible traces. The slow reveal theory within the zoo hypothesis suggests that a sudden, overwhelming contact with an advanced alien race might be too much for humanity to handle. Instead, these extraterrestrial watchers might choose to reveal their existence gradually, allowing us to adjust to the idea over time without causing societal upheaval. Then, there's the possibility of ancient taboos passed down through generations of alien cultures. These advanced civilizations may follow a strict rule against making contact with less developed worlds like ours. This cosmic code of non-interference may have originated with a powerful ancient civilization that set the standard, one that newer civilizations now choose to follow. The hands-off approach may also be tied to a deeper understanding of the risks. Risks that come with first contact, risks that we, as humans, may not yet fully comprehend. They may observe us silently, intervening only when absolutely necessary to prevent catastrophic events. The preservation hypothesis takes this a step further, suggesting that civilizations may wish to protect the unique cultural and technological diversity of the cosmos. Too much interaction between civilizations could lead to a blending of cultures, erasing the distinct traits that make each one unique. To avoid this homogenization, they may choose to stay isolated, observing each other from afar. Cultural factors such as xenophobia or religious beliefs within alien societies might also shape how or whether they interact with other civilizations. These cultural norms could explain long periods of silence or unpredictable responses to certain cosmic events. A more unsettling possibility is that intelligent life may be exceedingly rare, or perhaps we are alone. This rarity could either be a natural occurrence or the result of a dominant civilization suppressing the development of other intelligent beings. In this scenario, they maintain control by ensuring that no other species rises to challenge their supremacy. Alternatively, the universe itself might not be as it seems. What if it's a simulation, with Earth as the central focus of an experiment? This ties into the laboratory hypothesis, which proposes that our universe could be a carefully controlled environment created by unknown entities. The finely tuned nature of our universe could be a clue, and perhaps we are part of something far larger, an experiment in which we are the subjects and the watchers unseen. John Ball introduced a concept regarding the possibility of extraterrestrial beings attempting communication with us. He proposed that rather than trying to reach out, they may be deliberately avoiding contact. This idea is known as the zoo hypothesis. According to this theory, alien civilizations might be treating Earth as a protected area, similar to how we set aside land for wildlife or choose not to disturb isolated human groups. Ball speculated that advanced civilizations are quietly observing us from a distance, allowing humanity to evolve and grow on its own. He believed that they would only make contact when we reach a certain level of technological or political maturity. However, such an encounter might not be peaceful. It could lead to our civilization being overwhelmed, much like what has happened to isolated tribes when they came into contact with more developed societies. Ball also considered the idea that there could be a coalition of advanced civilizations that have agreed to treat planets like Earth as protected zones. This concept supports some similarity to the Prime Directive in Star Trek, a rule that forbids interference with less advanced societies. He emphasized that we should focus on the most advanced civilizations since they would likely be the ones making decisions. Unfortunately, like many theories about extraterrestrial life, the zoo hypothesis remains unprovable. It's as if we are living in a house where we can't tell if it's empty or filled with invisible, highly advanced beings. According to the zoo hypothesis, we may never discover these civilizations, not because they don't exist, but because they choose not to be found and possess the means to remain hidden. Each aspect of this hypothesis offers a different explanation for why we haven't encountered extraterrestrial life, providing various answers to the enduring questions posed by the Fermi paradox. Why haven't we found any signals from alien civilizations? The Great Silence raises a haunting question. In a universe so vast, with countless stars and planets, why do we hear nothing but silence? This absence of detectable signals from other civilizations challenges our understanding of the cosmos, where life seems so likely, yet remains unseen. In 1967, Jocelyn Bell, a young student at Cambridge University, stumbled upon something strange while using a radio telescope. She found a radio signal that pulsed regularly every 1.33 seconds. At first, scientists thought it might be some kind of interference, but the signal was too precise and came from deep space. The excitement grew, and the signal was even jokingly named LGM-1, short for a little green man, hinting at the hope that it might be from an alien civilization. However, this mystery soon found a natural explanation. The signal came from a pulsar, a type of neutron star spinning rapidly and emitting beams of radiation, much like a lighthouse casting its light across the sea. Despite such moments of excitement, our search for alien signals has turned up no clear evidence of extraterrestrial life. For about a century, humanity has been broadcasting radio signals into space. These signals now cover a bubble about 100 light-years wide. Within this bubble, alien civilizations might detect the faint hum of our broadcasts. But beyond this range, Earth quickly fades from view, and as our technology advances, we're sending fewer unintentional signals into space. Eventually, we may become radio silent. Radio signals weaken over time, and although our strongest emissions like military radar might reach farther, standard signals like TV broadcasts grow too faint to notice across the vast distances of space. However, new tools like the Square Kilometre Array being built in South Africa and Australia could allow us to detect signals from Earth-like civilizations hundreds of light-years away. We've also made direct attempts to reach out. In 1974, the Arecibo message was broadcast from Puerto Rico toward a distant star cluster. It was a focused, deliberate message designed to get the attention of any potential listeners. But even these efforts are brief, offering a small window for extraterrestrial observers to catch our signal. One of the most intriguing signals we've ever received is the 1977 WOW signal, a powerful burst of energy that remains unexplained to this day and has never been detected again. The odds of two civilizations randomly discovering each other through accidental broadcasts are incredibly small. To increase our chances, we need to focus our search on areas where we believe life is most likely to exist, and we need to search for signs of technology or biological life in space. In 1995, astronomers found the first planet orbiting a star like our Sun outside our solar system. Since then, we've learned that most stars in our galaxy have at least one planet. Many of these planets are similar to Earth, sitting in what is called the habitable zone around their stars and places where liquid water might exist, a key ingredient for life as we know it. Some moons orbiting these planets may also have the potential to support life. It's estimated there could be as many as 1 billion such moons across the galaxy. Recognizing this potential, scientists in 2017 sent a message to one of the closest Earth-like exoplanets we found. The message contained music and information about humanity, and if anyone is there and able to respond, we might hear back by 2044. To find out if these distant planets harbor life, scientists analyze the starlight passing through their atmospheres. If we find an atmosphere rich in oxygen, for example, it might be a clue that life exists there, as oxygen on Earth is mostly produced by plants. Still, oxygen alone doesn't prove life, as it can also come from natural processes. Astrobiologists focus on certain chemical combinations that likely wouldn't exist together without life, such as methane and oxygen. Other chemicals, like carbon dioxide, might suggest industrial activity or even climate change, which could signal intelligent life. By studying these chemical markers, scientists hope to find signs that life may exist beyond Earth. In addition to looking for biosignatures, scientists are also searching for technology-related clues called technosignatures. For example, an exoplanet with a dense field of artificial satellites or space debris could be spotted as it passes in front of its star. Another potential sign is a Dyson sphere, a massive structure theorized by physicist Freeman Dyson. These hypothetical megastructures might be built by advanced civilizations to gather energy from a star. The Kardashev scale, introduced by astrophysicist Nikolai Kardashev, ranks civilizations by their energy usage. A Type 1 civilization uses the energy of its planet, a Type 2 civilization gathers energy from its star, and a Type 3 civilization uses energy from an entire galaxy. Although we haven't found any proof of Type 2 or Type 3 civilizations in the Milky Way, these ideas inspire and guide the search for extraterrestrial life. Sometimes, strange astronomical events lead to speculations about alien life. For example, the unusual dimming of a distant star once sparked theories about alien megastructures blocking its light. However, this dimming is now believed to be caused by dust, not extraterrestrial construction. Despite such speculations, the search for solid proof of life beyond Earth continues. Astronomers remain fascinated by the search for life, especially advanced civilizations. After surveying 100,000 galaxies for evidence of a Type 3 civilization, no signs of such large-scale civilizations have been found. This widespread silence across the universe raises some intriguing questions, especially since Earth has been releasing detectable biosignatures for about 1 billion years without drawing any apparent attention from alien life. This contradiction between the likelihood of extraterrestrial life and the lack of evidence is known as the Fermi paradox. One explanation for this could be that life, especially intelligent life, is extremely rare. The long, complex evolutionary history of Earth, including multiple mass extinctions before humans appeared, supports the rare Earth hypothesis. This idea suggests that the development of complex life on Earth required a series of unlikely events that may not have occurred elsewhere in the universe. Another possibility is the existence of a great filter, a significant barrier to the development of life. If this barrier is behind us, then Earth may be one of the few planets that has passed it. However, if the filter lies in the future, humanity could face a major challenge that could end life as we know it. The nature of alien life itself is another mystery. While life on Earth is carbon-based and relies on water, alien life forms could be entirely different, such as life based on silicon or living in ammonia oceans. This could mean we're overlooking signs of life because we're only searching for life that resembles our own. Despite these challenges and uncertainties, the search for extraterrestrial life continues to drive scientific research, expanding our knowledge and pushing the limits of what we understand about the universe. Nothingness, an absolute void, is a concept that challenges the human mind. We often assume that everything must come from something, but how did everything begin? We sometimes claim it started from nothing, but how can nothing become something? In the vastness of the cosmos, where galaxies shine and black holes pull in matter, the idea of nothingness stretches our understanding of the universe. This isn't just a philosophical question, it's a core idea in cosmology that has intrigued scientists and thinkers for centuries. Imagine a region of space completely free of stars, planets, or any form of matter. A quiet stretch of the universe where the usual rules of physics may no longer apply. Though it seems contradictory, nothingness plays an essential role in our understanding of the universe. To grasp the mysteries of the cosmos, we must first understand what nothing means in the context of space. At first glance, the emptiness of space might seem like a perfect vacuum with no matter or energy. While there is some truth to this idea, it doesn't capture the full picture that modern science has revealed. In today's understanding, nothingness is not an empty void, but a dynamic space filled with unexpected activity. Let's dive into this idea through the lens of science. Contrary to what we might think, space is not truly empty. It is alive with quantum fluctuations, where particles and antiparticles briefly pop into existence, only to cancel each other out. This gives the vacuum a constantly changing nature. Even in areas with no visible matter, space is linked to the fabric of space-time, as described by Einstein's theory of general relativity. Massive objects, like stars or black holes, can still bend space-time, affecting how things move around them. When we peer into the depths of space, we can detect the faint afterglow of the Big Bang, the cosmic microwave background radiation. This relic from the early universe reminds us that space has changed over time. Yet, despite our progress, the idea of nothingness remains a deep puzzle, one that both scientists and philosophers continue to ponder. Some theories suggest that there might be parts of the universe where the density of matter is incredibly low, close to absolute nothingness. While these ideas remain largely speculative, they point to the possibility of vast voids in space. If such regions exist, they could help us better understand the true nature of space. Is empty space really devoid of all matter and energy? This question, which seems simple on the surface, leads to a wealth of scientific and philosophical inquiry. Traditionally, we think of space as an empty vacuum, a blank canvas without matter or energy. This fits with our basic idea of emptiness, but the deeper we go into the study of the universe, the more we find that reality is far more complex than we once thought. In quantum mechanics, which explains the behavior of particles at the smallest scales, we encounter another challenge to our idea of nothingness: quantum fluctuations. These suggest that even in the emptiest parts of space, particles and antiparticles can appear, briefly interact, and then vanish again. These momentary events give the void a kind of restless energy, challenging our understanding of what it means for something to be truly empty. Additionally, Einstein's theory of general relativity shows us that space and time are woven together into a four-dimensional fabric called spacetime. Massive objects like planets or stars can bend this fabric, pulling nearby objects toward them. So the idea of a completely empty, untouched space becomes harder to imagine. How does the idea of nothing connect with dark matter, and what does it reveal about the universe's structure? To answer this, we first need to understand dark matter itself. Unlike the ordinary matter that makes up stars, planets, and galaxies, dark matter remains invisible, only making itself known through the gravitational forces it exerts. It represents the ultimate form of nothingness, as it escapes direct observation and doesn't fit traditional definitions of matter. Dark matter's existence was suggested by observing galaxies and their movements. The gravitational pull from visible matter alone couldn't explain their behavior. To account for this gap, scientists proposed the presence of an unseen, intangible substance, dark matter, that fills cosmic spaces and holds galaxies together. The Big Bang theory suggests that the universe began about 13.8 billion years ago, starting from a singularity, a point of infinite density and temperature. This moment marked the birth of space and time itself, emerging from what might seem like nothing in conventional terms. But how does this explosive start connect with the idea of nothingness? To understand, we must look closer at the nature of the singularity. A singularity represents a state where the normal laws of physics don't apply, a point with infinite density and zero volume, defying our usual ideas of matter and space. In this way, the singularity reflects a form of nothingness, where the universe lacked the familiar structure and dimensions we recognize. However, this nothingness was packed with potential. As the universe expanded from this singularity, it went through a rapid phase of inflation, causing space to stretch almost instantly. This expansion transformed the universe from a state of near-nothingness into a space filled with energy, particles, and forces that shape the cosmos as we know it. In the early moments after the Big Bang, the universe was extremely hot and dense, like a thick soup of particles and radiation. In less than a second, it underwent a series of changes, including nucleosynthesis, where the first atomic nuclei came together. This evolution paved the way for stars, galaxies, and the intricate structure of the universe we see today. How do we know the Big Bang happened? There is plenty of evidence supporting this idea. One key clue is the cosmic microwave background radiation, a faint afterglow left over from the early universe. This radiation gives us a picture of the universe as it looked about 380,000 years after the Big Bang, when it finally cooled enough for light to travel through space. In 1965, Arno Penzias and Robert Wilson found this radiation by accident, providing strong support for the Big Bang theory. The even spread of the CMB and its small variations support the idea of cosmic inflation, a period of rapid expansion in the early universe. Another key piece of evidence is the redshift of galaxies. This redshift shows that galaxies are moving away from us, indicating that the universe is expanding. In the 1920s, Edwin Hubble first observed this, and he noticed that the farther away a galaxy is, the faster it moves away, backing up the idea that the universe started small, hot, and dense. However, the Big Bang theory leaves some major questions unanswered. For instance, it doesn't explain what came before the Big Bang or what lies beyond the edge of the observable universe. It also introduces the idea of cosmic inflation, a phase of rapid growth right after the Big Bang, which still puzzles scientists. Before the discovery of the cosmic microwave background radiation, there was another popular theory called the steady-state theory. This theory suggested that the universe has no beginning or end, but stays the same overall, even though it expands, by constantly forming new matter. This idea was well known in the 1940s, but lost support after the CMB radiation was found in 1965, giving strong backing to the Big Bang theory. There are also other ideas, like the cyclic model, which suggests that the universe goes through endless cycles of expansion and shrinking. After the Big Bang, the universe kept expanding and cooling. In the beginning, it was a hot, dense mix of particles. As it spread out, it cooled, allowing particles to join together and form the first atoms. These atoms eventually formed the first stars and galaxies, and the universe's expansion continues today, with galaxies moving away from us in all directions. Going back to the earliest moments of the universe, the first long-lasting particles were protons and neutrons, which formed the nucleus of atoms. These particles appeared around 1/10,000th of a second after the Big Bang. Before this, there was no material in the way we understand it. However, physics allows us to trace the timeline even further back to events that occurred before stable matter existed. To grasp how the universe could begin from nothing, we need to explore the strange world of quantum mechanics. In quantum physics, nothing isn't an empty void, but rather a state of vacuum energy, where particles constantly appear and vanish. This is known as quantum fluctuations. Quantum fluctuations happen in a state called the quantum vacuum, which has the lowest possible energy level. In this state, particles can momentarily come into being and then disappear. According to quantum mechanics, these fluctuations can, in theory, lead to the creation of a universe. So, in this context, nothing is an energetic state that has the potential to bring matter and energy into existence. A key idea here is Heisenberg's uncertainty principle. This principle states that certain pairs of physical properties, like position and momentum, cannot both be measured with complete accuracy at the same time. This principle allows particles to briefly pop into existence from the vacuum as long as they disappear quickly enough to respect the law of conservation of energy. These quantum fluctuations cause particles to appear and vanish shortly afterward. While this might sound strange, such particles have been observed in many scientific experiments. The vacuum of space is filled with particles constantly being created and destroyed, suggesting that the quantum vacuum is not truly empty. But where did space-time itself come from? To answer this, we need to look back to the very beginning of the universe into a period called the Planck epoch. This phase occurred so early in the universe's history that our current theories of physics stopped working. It happened only a tiny fraction of a second after the Big Bang. During this time, space and time were affected by quantum fluctuations. Usually, scientists rely on quantum mechanics to explain tiny particles and on general relativity to explain the large-scale structure of the universe. But to understand the Planck epoch, we need a theory that combines both, something known as quantum gravity. We don't have a complete theory of quantum gravity yet, but there are ideas like string theory and loop quantum gravity. These theories suggest that what we experience as space and time may come from deeper, microscopic processes. The space and time we're familiar with are the result of these quantum processes, which are difficult for us to understand because we live in a world of large-scale objects. Quantum fluctuations occur constantly, even in what we consider to be empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can appear from the vacuum, exist for a brief moment, and then cancel each other out. This process is sometimes called quantum foam. However, quantum fluctuations alone don't explain the vast scale and complexity of the universe. There is also dark energy, a mysterious force that fills all of space and speeds up the expansion of the universe. While we don't fully understand dark energy, it seems to play a key role in the creation and growth of the cosmos. So, how did we get from quantum fluctuations and dark energy to the universe we see today, filled with galaxies, stars, and planets? The answer lies in inflation, a period of rapid expansion that took place fractions of a second after the Big Bang. During this brief time, the universe expanded at an incredible rate, setting the stage for the formation of everything we observe today. In the Planck epoch, our normal understanding of space, time, and cause and effect breaks down. Despite this, all the leading theories of quantum gravity suggest that something physical was happening during this period, some quantum process that led to the space and time we know. But where did this come from? That remains one of the universe's most profound questions. Even though causality might not function in the way we typically understand, there is still hope that parts of the Planck epoch universe could explain other parts. Unfortunately, our current understanding of physics cannot yet provide clear answers. Until we develop a complete theory of everything, we won't be able to give a definite explanation. What we do know for certain is that no confirmed instance of something emerging from absolute nothing has been found. In this context, the idea of nothingness becomes more dynamic and complex. It is not a simple, empty void, but rather a canvas where the universe paints its story. A story that began with the explosive birth of the cosmos. One of the key questions in advanced cosmology is whether the vacuum of space is truly empty or whether it still contains particles or fields. At first glance, we might imagine space as a vast, empty expanse with no matter or energy. Yet, when we dive into the strange world of quantum mechanics, we discover something surprising. Space is not as empty as it might seem. Quantum mechanics, which explains how particles behave on the smallest scales, shows us that space is full of activity, even in what we think of as emptiness. The vacuum of space is not silent, it's alive with quantum fluctuations. These fluctuations are like tiny ripples on a calm pond, appearing at the subatomic level. In these fluctuations, particles and their opposites briefly appear, interact, and then disappear again, creating a fleeting dance of existence. These momentary events challenge our classical view of emptiness, revealing that the vacuum is constantly shifting and changing. In addition, the vacuum of space is not just an empty background, but plays an essential role in the universe. It hosts fields that control the fundamental forces, such as the electromagnetic field. These fields stretch across space, even in regions we think of as empty. In advanced cosmology, we learn that the vacuum is far from a simple void. It is a lively space, filled with quantum fluctuations and fields, blurring the line between nothing and something, and forcing us to rethink what emptiness really means. This idea also has real-world implications. Scientists have found ways to use the energy within these quantum fluctuations in a phenomenon called the Casimir effect. When two parallel conducting plates are placed very close together in a vacuum, they experience a small but measurable attraction due to the changes in the quantum fluctuations between them. This effect, though tiny, shows that the concept of nothingness in space can have real and measurable consequences. To truly answer how something could arise from nothing, we first need to explore several different interpretations of nothing. This interpretation describes a state where the essential building blocks of everything we see are absent. Imagine a universe without galaxies, stars, planets, or humans. Everything we interact with is made up of tiny subatomic particles, the fundamental components that shape the universe. Starting with a universe full of matter, we understand how it grows, cools, and becomes influenced by gravity, eventually forming the universe we know today. Stars live through cycles, creating heavier elements that lead to new stars, planets, and life. But one of the biggest questions in science remains: how did we end up with a universe dominated by matter, rather than equal amounts of matter and antimatter? This is one of the great unsolved mysteries in physics. The universe is almost entirely made of matter, with hardly any antimatter. So, how did we end up with this imbalance of matter? This puzzle is called baryogenesis, the process that created more baryons than antibaryons in the early universe. While there are many theories, we still don't have a clear answer as to why matter dominates over antimatter. Our second interpretation considers nothing as the emptiness of vast space. If you think of nothing as having no things at all, then the first interpretation, where particles are just missing, doesn't fully capture this idea. To understand this concept of nothingness, we need to imagine removing every single particle and all energy from space. If we manage to strip away all matter and energy, what remains is the empty expanse of space. No particles, no matter, no radiation. This is what some scientists regard as true nothingness. However, space-time itself, shaped by general relativity, still exists. The speed of light and the gravitational constant remain the same. There is also something called zero-point energy. Even in the most empty space, a small amount of energy remains. Today, we associate this with dark energy, which causes the universe to expand. But even in this extremely empty scenario, some fundamental elements remain. The laws of physics still exist. Quantum fields, such as the electromagnetic field, gravitational field, and Higgs field, are still present. So, even without matter or radiation, this version of nothing still gives rise to an intriguing universe. It's fascinating to realize that even in the absence of all the things we can see, the universe remains a lively and dynamic place. The third interpretation of nothing considers it as the lowest energy state possible. Right now, our universe has what's known as zero-point energy, a small amount of energy that exists everywhere in space. We don't know if this zero-point energy represents the absolute lowest energy possible, or if there could be an even lower energy state waiting to be discovered. We might be living in a false vacuum, with the true vacuum, the absolute lowest energy state, still out there. If the universe shifted from this false vacuum to a true vacuum, it could trigger a catastrophic event known as vacuum decay. This would fundamentally change the universe. Light particles would gain mass, the electromagnetic force would become limited to short distances, and most of the sunlight would no longer reach Earth. Thinking of nothing as the ultimate lowest energy state means imagining a scenario where all matter, energy, radiation, and any warping of space-time have been removed. What remains is a state of pure emptiness, though the laws of physics would still be present. In this state, it would be impossible to create work, energy, or particles. However, some would argue this still isn't truly nothing because space-time and the rules of physics still exist. It would be like a stage with no actors or plot, just an empty backdrop. So, our third interpretation of nothing is the ultimate lowest energy state possible for the universe. Even in this state, the structure of space, time, and the laws of physics remain intact. It's another incredible mystery that keeps scientists searching for answers. Fourth interpretation of nothing. This is the most extreme interpretation of nothing. It suggests that true nothingness only happens when the entire universe and the rules that govern it completely disappear. This idea goes beyond anything we usually understand. Imagine removing everything including space, time, and even the laws of physics. This kind of nothing cannot be defined by the rules of physics because it represents an absolute void, a total absence of everything. From a scientific perspective, this concept is hard to grasp. How could space-time exist without space or time? How could the laws of physics operate without a structure for them? This version of nothing is difficult to imagine and may not have any real-world meaning. Thinking about this kind of nothingness raises many questions without clear answers. For instance, how could space and time begin from a state where they don't exist? Is it possible to have something without space or start without time? Picture an absolute void known as a complete nothingness. From a physics viewpoint, it hints at a state beyond space and time from which the universe and its rules might have emerged. However, it's unclear if this idea is meaningful or just a product of our imagination. This concept introduces difficult questions. How could space and time begin in a place where neither exists? Could something exist outside the universe or start without time? Where would the rules that control particles and their interactions come from? While this idea of nothingness seems complete, it may not have any real substance. It might simply be a way for us to think about things that are beyond our experience. When scientists talk about nothing, they often assume that everyone shares the same idea of what it means. But that's not always the case. Different people and contexts can shape how we understand nothing. While theories about nothing are grounded in scientific studies, the study of the cosmic microwave background radiation or the faint afterglow of the Big Bang provides key insights into the conditions of the early universe. Precise measurements of the CMB have given us a better understanding of the age, makeup, and structure of the universe. Observations of the expanding universe, as described by Hubble's law, support the idea that the universe began from a hot, dense state. The discovery of dark matter and dark energy, which make up most of the universe's mass and energy, also shows that our understanding of the universe is still incomplete. The phrase "something from nothing" might refer to creating something entirely new where there was truly nothing before. But not everyone agrees on what nothing really means. So, it's important to clarify which version of nothing is being discussed. Philosophically, nothing can be even more abstract. Some philosophers argue that true nothingness is an absolute void, completely without properties or existence. Others suggest that even in a state of nothingness, there might be some potential or possibility that allows something to emerge. When we look at the evidence from cosmic microwave background radiation or quantum fluctuations, we don't get answers about what existed before the Big Bang. One of the biggest mysteries in cosmology is the question of what existed before the Big Bang and what created the singularity that led to it. The Big Bang theory tells us that the universe began from an incredibly dense and hot point called a singularity. A singularity is a place where all the rules of space and time fall apart, including the laws of physics. If the usual laws of physics don't work in a singularity, What rules apply? To understand this, let's look at Albert Einstein's ideas. His theory of relativity changed how we think about the universe by linking mass and time. According to this theory, time isn't fixed but changes based on the gravitational pull of massive objects. Einstein showed that large objects like Earth can slow time down. Now, if mass slows down time, imagine what the singularity does, since it contains all the mass in the universe. It would stop time completely. So, according to Einstein, asking what happened before the Big Bang doesn't make sense, because time itself didn't exist before that moment. The cosmic microwave background radiation is an important piece of evidence. It comes from a time about 380,000 years after the Big Bang, when the universe was cooling and hydrogen atoms were forming. Before this point, the universe went through several stages, from the Planck epoch to the Grand Unification, Inflationary, Electroweak, Quark, and Hadron epochs. Each of these phases led to different particles and forces forming the universe we know today. When we look at the universe on such a small scale, quantum mechanics takes over from classical physics. This led scientists like Stephen Hawking to consider how quantum theory could apply to the entire universe. This is where inflationary quantum cosmology comes into play. Unlike classical theories that describe the singularity as a point with no volume, quantum cosmology suggests there's a level of uncertainty. This means we can't pinpoint the exact moment the universe came into being, and particles can appear and disappear in what we call a vacuum. In physics, a vacuum isn't a state of complete emptiness but a place without particles. According to Heisenberg's uncertainty principle, there's always some level of fluctuation, so a perfect vacuum with no energy is impossible. This may sound unusual, but Einstein's famous equation helps explain it. The positive energy in stars and galaxies must be balanced by an equal amount of negative energy, like gravity. If the total energy of the universe is zero, then it's possible for it to have come from nothing. The idea that hundreds of billions of galaxies could come from nothing seems hard to believe. However, Einstein's equation gives us clues. According to the equation, the positive energy in stars, galaxies, and other cosmic objects must be balanced by an equal amount of negative energy, which appears as gravity. In a closed universe, the positive and negative energies would cancel each other out, leaving the total energy of the universe at zero. Stephen Hawking asked how a universe with zero total energy could come from nothing. He suggested that the negative energy of gravity could balance the positive energy needed to create matter. This idea makes the empty space stable. Physicist Alexander Vilenkin expanded on this, showing that a small, energy-filled vacuum could spontaneously form from nothing and expand into the universe we know today. This suggests that our universe could have started from a state of nothing, where even time didn't exist. Another interesting possibility is the multiverse hypothesis, which suggests that our universe is just one of many that exist. In this idea, the Big Bang that created our universe may have been just one of many similar events happening within a larger multiverse. In this scenario, new universes could be constantly forming, each with its own physical laws and constants. These universes might be created through different processes, like quantum fluctuations or collisions between higher dimensional membranes in string theory. This means that the beginning of our universe could have been just one event in an endless cycle of creation and destruction. Some theories in physics suggest that higher dimensions beyond our familiar 3 dimensions of space and one of time might have played a key role in the universe's origin. For example, string theory proposes that the basic building blocks of the universe are tiny, one-dimensional strings that vibrate in multiple dimensions. In this framework, our universe could be a 3-dimensional brain floating in a space with even more dimensions. Collisions or interactions between these brains could trigger events like the Big Bang, giving birth to new universes. So, what was there before the Big Bang? The ideas we've looked at suggest that time itself began with the Big Bang, which makes the question of before tricky to answer. From singularities to quantum fluctuations, these theories reveal just how incredible and mysterious our universe really is. The Big Bang Theory explains how the universe expanded from a superhot, dense state, but it doesn't tell us what happened before that. According to the theory, time, space, matter, and energy all began with the Big Bang. However, some scientists have explored what might have existed before the Big Bang. One interesting idea is the Big Bounce, which suggests that the universe goes through cycles of expanding and contracting. So, the Big Bang we know could have been just one of many, with the universe being constantly reborn. Another intriguing idea is the concept of a multiverse. This theory proposes that our universe is just one of many, each with its own set of physical laws. In this model, what existed before our Big Bang could have been another universe entirely. These ideas stretch the limits of what we currently understand and venture into speculative territory. They rely on advanced concepts in quantum physics and the still developing area of quantum gravity. Scientists are working to connect quantum mechanics and general relativity to better explore these possibilities. After the Big Bang, the universe continued to expand and cool. At first, it was a soup of tiny particles. As it cooled further, these particles came together to form the first atoms, mainly hydrogen and helium. While these theories offer exciting glimpses into what might have been before the Big Bang, they are still mostly theoretical, highlighting the deep mystery surrounding the universe's origins. As we look back through time, we can trace the development of cosmic structures, but each new discovery brings another question. Where did this come from, and how did it form? These questions eventually lead to the point where the only honest answer is, we don't know, at least not yet. With the knowledge we have, we can still ask, how did all of this come to be? The life we see today relies on complex molecules which evolved from the simple atoms that make up the periodic table. These atoms are the building blocks of all ordinary matter in the universe. However, they weren't present at the very beginning of the universe. They'd formed through cycles of stars being born, living, and dying. Each cycle of stellar life contributed to nuclear reactions that produced these atoms, which were then recycled into newer stars. Without this ongoing process, the creation of planets and the chemistry needed for life would not have been possible. To understand how the stars and galaxies we see today formed, a few key elements must fit together. Gravity plays a huge role. It pulls together small groups of stars and galaxies to form the large galaxies we see now, sparking new star formation. For gravity to work, there must already be enough mass clumped together. This is where dark matter becomes important. Early in the universe, dark matter formed halos that helped prevent the newly formed stars from scattering their material back into space. Additionally, the right mix of matter, like atoms, dark matter, and radiation, was crucial. This mix not only produced the cosmic microwave background, the afterglow of the Big Bang, but also helped form the light elements during the hot, dense state of the early universe. The growth of galaxies and star clusters depended on small initial differences in density, often called seed fluctuations, which grew under the pull of gravity. Finally, there must have been processes that created these initial density variations, dark matter, and the first bits of ordinary matter. To understand how our universe came to be from the chaos of the Big Bang, we must consider some key conditions present from the start. The laws of physics, the structure of space-time, and the matter-energy content of the universe had to emerge from something, but exactly how remains one of the greatest confuses in science. Do you ever wonder how the universe has reached the point where its boundary stretches across billions of light years? To answer that question, we must go back to the very beginning, the birth of the universe. One of the most important questions in cosmology is how it all began. One of the main theories in modern cosmology is the Big Bang theory, which explains how our universe started and evolved. Imagine every star, planet, and galaxy compressed into an incredibly hot and dense point. Scientists believe this is how everything began about 13.8 billion years ago. From this tiny, dense point, the universe began to expand and cool. This event, called the Big Bang, marks the beginning of the universe's growth and the enormous distances we see today. The term Big Bang can be misleading, as it suggests an explosion happening in space. However, it wasn't an explosion in space, it was the expansion of space itself. In the first fractions of a second after the Big Bang, the universe expanded rapidly in a phase called cosmic inflation. During this short period, the universe grew from an almost unimaginably small point to a size we can observe today. As the universe expanded, it cooled, allowing energy to turn into particles of matter. These particles came together to form simple elements like hydrogen and helium. Over billions of years, these elements merged under gravity to form stars, galaxies, and planets. The formation of these elements happened within the first few minutes after the Big Bang, as the universe cooled enough for protons and neutrons to form atomic nuclei. The Big Bang theory is backed by strong evidence. One key piece is the cosmic microwave background radiation, which is like a faint afterglow from the early universe. This radiation gives us a picture of the universe about 380,000 years after the Big Bang, when it had cooled enough for light to travel through space. The uniformity and slight differences in the CMB support the idea of cosmic inflation and the universe's rapid expansion. Another piece of evidence is the redshift of galaxies. This redshift shows that galaxies are moving away from us, which means the universe is expanding. This was first observed by Edwin Hubble in the 1920s. The farther away a galaxy is, the faster it seems to be moving away from us, showing that the universe was once much smaller, hotter, and denser. While the Big Bang theory explains the universe's expansion and development, it raises more questions. For example, it doesn't tell us what lies beyond the observable universe. The idea of cosmic inflation suggests a rapid expansion right after the Big Bang, but it leaves open questions about what the universe is like beyond what we can observe. Before the discovery of the CMB radiation, there was another theory called the steady-state theory. This theory suggested that the universe had no beginning or end and stayed the same overall, even while expanding by constantly forming new matter. This idea was popular in the 1940s, but lost support after the CMB radiation was discovered in 1965, which strongly supports the Big Bang theory. Other ideas, like the cyclic model, suggest that the universe goes through endless cycles of expansion and contraction. After the Big Bang, the universe continued expanding and cooling. Initially, it was a hot, dense mix of particles. As it expanded, it cooled, allowing particles to come together and form the first atoms. These atoms then formed the first stars and galaxies. The universe's expansion continues today, with galaxies moving away from us in all directions. If we think even further back, the first stable particles, protons and neutrons, which make up atomic nuclei, appeared about 1/10,000th of a second after the Big Bang. Before that, there was no material as we know it. Physics allows us to trace the timeline even further back to events that occurred before stable matter existed. The observable universe includes all the matter and energy we can detect from Earth, limited by the speed of light and the universe's age. Since the universe is about 13.8 billion years old, we can only observe light that has traveled up to 13.8 billion years to reach us. However, due to the universe's expansion, the observable universe stretches far beyond 13.8 billion light-years. The radius of the observable universe is believed to be about 46.5 billion light-years, giving it a diameter of about 93 billion light-years. Despite this enormous scale, the observable universe is only a fraction of the entire universe. The actual size of the universe is unknown and could be far larger than what we can see. The expansion of the universe means that objects near the edge of the observable universe are moving away from us faster than the speed of light, making it impossible to observe anything beyond this horizon. The universe has been expanding since the Big Bang, and this expansion affects how we observe it. Galaxies are moving away from each other, with the space between them stretching. This means the observable universe is continuously growing as light from more distant areas reaches us over time. Within the observable universe, scientists estimate there are about 2 trillion galaxies, each containing billions of stars. These galaxies come in various forms, from spirals like our Milky Way to elliptical and irregular shapes. With so many stars, it's possible that countless planetary systems exist, and some may even support conditions suitable for life. One of the most remarkable images captured by the Hubble Space Telescope is the Hubble Deep Field, which shows a tiny patch of the sky filled with thousands of galaxies. Each galaxy holds countless stars, planets, and perhaps even life. This image represents only a small fraction of the sky, highlighting the vast number of galaxies that exist within the observable universe. To understand how the universe could emerge from nothing, we need to explore the strange world of quantum mechanics. In quantum physics, nothing is not the absence of everything, but rather a state of vacuum energy where particles constantly appear and disappear. This is known as quantum fluctuations. Quantum fluctuations happen in what is called the quantum vacuum, a state with the lowest possible energy where particles briefly emerge and then vanish. According to the laws of quantum mechanics, these fluctuations can, in theory, lead to the creation of a universe. In this way, nothing becomes a state that can give rise to matter and energy. One of the key ideas that helps explain this process is Heisenberg's uncertainty principle. This principle says that certain physical properties, like position and momentum, cannot both be known with absolute precision at the same time. Because of this principle, particles can briefly emerge from the vacuum as long as they disappear quickly enough to follow the law of conservation of energy. Quantum fluctuations can cause particles to appear and vanish shortly after. While this may seem strange, these particles have been observed in many experiments. The vacuum of space is filled with particles constantly being created and destroyed, suggesting that the quantum vacuum is not empty at all, but active. But where did spacetime itself come from? To answer this, we must go back to the very beginning, to a period called the Planck epoch. This phase occurred in the earliest moments of the universe, so early that our current physics cannot fully explain it. It happened only a tiny fraction of a second after the Big Bang. During the Planck epoch, space and time were influenced by quantum fluctuations. Normally, quantum mechanics explains the behavior of tiny particles, while general relativity explains larger scales. But to understand the Planck epoch, we need a complete theory of quantum gravity that combines both. While we don't yet have a perfect theory of quantum gravity, there are ideas such as string theory and loop quantum gravity. These theories suggest that space and time, as we experience them, emerge from deeper, more complex processes at the quantum level. It's hard for us to grasp these ideas because we are used to thinking in terms of large-scale objects. Quantum fluctuations occur constantly, even in what seems to be empty space. According to the Heisenberg uncertainty principle, pairs of particles and antiparticles can emerge from the vacuum, exist for a brief moment, and then destroy each other. This process is known as quantum foam. However, quantum fluctuations alone cannot explain the vast complexity of the universe. There is also dark energy, a force that fills all of space and speeds up the expansion of the universe. While we don't fully understand dark energy, it plays a key role in shaping the cosmos. So how did we go from quantum fluctuations and dark energy to the structured universe we see today? The answer lies in a rapid expansion that occurred just after the Big Bang, called inflation. During this brief moment, the universe expanded at an exponential rate, setting the stage for the formation of galaxies, stars, and planets. Over time, due to dark energy, these celestial objects began to move apart instead of pulling toward each other, leading to the universe's continued expansion. Dark energy counteracts gravity, causing the universe to expand at an increasing rate. This means galaxies aren't just moving apart, but doing so at faster speeds. In the distant future, this could lead to galaxies moving so far apart that they become isolated, leaving the universe a much lonelier place. In conclusion, the birth and expansion of the universe involve complex processes shaped by quantum mechanics and cosmic forces like dark energy. From the Big Bang and cosmic inflation to the ongoing expansion driven by dark energy, these phenomena have formed the universe we see today. black holes are among the strangest objects in the universe. They are regions where matter has been compressed to such an extreme degree that the gravitational pull becomes so strong that not even light can escape. Black holes are often thought of as ultimate voids, giving a new dimension to the concept of nothingness. At the heart of a black hole lies a singularity where density becomes infinitely high and the rules of physics as we know them no longer apply. This singularity can be seen as a counterpart to the nothingness that may have existed before the Big Bang. While black holes form from the remains of massive stars, the absence of matter within them and their powerful gravitational fields make them fascinating subjects when considering the universe's formation from nothing. Black holes form when massive stars use up their nuclear fuel and collapse under their own gravity. This collapse leads to a supernova, leaving behind a dense core that can become a black hole. Black holes play a significant role in the evolution of galaxies and the broader cosmos. They are often found at the centers of galaxies, including our own Milky Way, where they influence the motion of stars and gas. Supermassive black holes, with masses millions or even billions of times greater than the Sun, shape the dynamics of their host galaxies. The interactions between black holes and their surroundings provide important insights into the formation of cosmic structures, helping us understand how the universe evolved from a state of apparent nothingness. The idea of nothingness has been a subject of philosophical thought for centuries. Philosophers have long debated the nature of existence and the possibility of a state without anything. In cosmology, nothingness refers not only to the absence of matter, but to a state where space and time themselves do not exist. This idea challenges our everyday experiences and pushes the boundaries of human understanding. Some philosophical viewpoints argue that nothingness is impossible, as the concept itself suggests the potential for something to exist. Others suggest that the universe's emergence from nothingness highlights the complexity of reality, where even the absence of things can lead to everything we observe. Science also explores nothingness, often intersecting with philosophical ideas, particularly when discussing the origins of the universe. In physics, nothingness can be described as a quantum vacuum, where particles and antiparticles appear and disappear constantly. This dynamic vacuum challenges the traditional idea of an empty void, suggesting that even space is full of potential activity. Theories like quantum field theory and quantum mechanics describe the probabilistic nature of particles and their interactions. The possibility that the universe could emerge from a quantum vacuum supports the idea that nothingness is not a static state, but one filled with potential for creation and transformation. The implications of nothingness reach beyond theoretical physics and cosmology. Understanding how the universe might emerge from nothingness can change our views on existence, creation, and reality itself. It challenges the conventional distinction between something and nothing, showing that the potential for existence may be embedded in the very nature of reality. This realization can also have profound philosophical and existential effects, influencing how we see our place in the universe and what existence means. Additionally, studying how the universe began from nothingness can drive new discoveries and innovations as we continue to unravel the mysteries of the cosmos and our beginnings. The concept of nothing has changed significantly over time, reflecting advances in both scientific and philosophical thought. In ancient times, nothingness was often associated with a complete void, without matter, energy, or space. However, as our knowledge of the universe grew, the idea of nothingness became more complex. Quantum mechanics introduced the idea that even in a vacuum, particles and antiparticles could appear and disappear, showing that nothing is not truly empty. This new understanding has important implications for how we think about the origins of the universe, emphasizing the dynamic nature of what we once considered a static void. As we explore the universe, our understanding of nothingness continues to evolve. The discovery that the universe is expanding, made by Edwin Hubble in the 1920s, revolutionized cosmology. This finding suggested that the universe had a beginning, which emerged from a singularity. This led to the development of the Big Bang Theory, which describes how the universe began as a hot, dense point and has been expanding ever since. This theory suggests that before the Big Bang, there was a state of nothingness from which everything emerged. The idea that the universe could come from a quantum vacuum challenged traditional views and opened new paths for understanding the nature of reality. Revolutionary insights into nothingness have come from various areas of science, especially quantum mechanics and cosmology. One key idea is quantum fluctuations, which occur even in a perfect vacuum. These fluctuations cause temporary changes in energy that create particles and antiparticles, providing a possible explanation for how the universe could emerge from nothing. Additionally, the concept of cosmic inflation, a rapid expansion that took place right after the Big Bang, helps explain how quantum fluctuations may have grown into large-scale structures like galaxies. These insights have reshaped our understanding of nothingness, showing that it may be the starting point for the universe itself. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided key evidence for the Big Bang Theory. The CMB is the faint afterglow of the Big Bang, filling the universe and giving us a glimpse of the cosmos about 380,000 years after its beginning. The uniformity of the CMB, along with its tiny temperature variations, reveals the early structure of the universe, supporting the idea that it started from a hot, dense state and expanded over time. This discovery was crucial in confirming the Big Bang model and advancing our understanding of how the universe could arise from a state close to nothingness. The concept of nothing is inherently puzzling, as we tend to think in terms of things that exist or don't exist. The idea of nothingness challenges the way we normally understand reality, forcing us to explore the limits of our thinking. In cosmology, this puzzle is seen in the idea that the universe could emerge from a quantum vacuum, a state that is not truly empty but filled with potential. The difficulty lies in reconciling the presence of the universe with the idea of a prior state of nothingness. This tension drives both scientific inquiry and philosophical debate, pushing us to refine our ideas and expand our knowledge. Quantum fluctuations in the vacuum offer an intriguing view of how the universe might have emerged from nothing. In quantum field theory, even in what seems to be a perfect vacuum, particles and antiparticles constantly appear and disappear due to energy fluctuations. These fluctuations are not random. They follow the principles of quantum mechanics, which allow for temporary shifts in energy. This active vacuum can give rise to a range of phenomena, including the formation of the universe. During the universe's early moments, these fluctuations were amplified by a period of rapid inflation, leading to the creation of matter and energy from what was once considered empty space. This process shows that what we think of as nothing is actually a dynamic space full of quantum activity capable of bringing the universe into being. Philosophically, nothingness has long been a subject of deep thought and debate. The idea challenges our basic understanding of existence and reality. In classical philosophy, nothingness was often seen as an absolute void, lacking matter, space, and time. However, modern physics has complicated this view by suggesting that nothingness may not be truly empty, but instead full of quantum potential. This shift challenges our understanding of what it means for something to exist, implying that even when matter and energy are absent, the universe still has the potential for creation. These reflections encourage us to rethink the nature of reality and the limits of our knowledge. Human senses are naturally limited when it comes to perceiving nothingness. Our senses detect matter and energy, such as light, sound, and heat. The concept of nothingness in physics often goes beyond what we can directly experience. For example, quantum fluctuations and the cosmic vacuum cannot be sensed directly but are inferred through advanced instruments and mathematical models. This gap between our intuitive understanding and scientific reality highlights the need for sophisticated tools and abstract thinking to understand concepts that lie beyond our everyday experience. Quantum phenomena present significant challenges to our understanding of nothingness. Quantum mechanics reveals that particles can exist in more than one state at the same time and can interact across great distances. These phenomena defy classical ideas of cause and effect, making it difficult to grasp how the universe could begin from a state of nothingness. The idea that quantum fluctuations could lead to the creation of the universe requires us to align these phenomena with the idea of a vacuum. This complexity highlights the challenges of quantum mechanics and its role in shaping our understanding of the cosmos, pushing both science and philosophy to their limits. Cognition and abstract thinking play a key role in our efforts to understand nothingness and the origins of the universe. Human thought is well suited to dealing with concrete experiences, but struggles with abstract concepts like the emptiness from which the universe might have emerged. Theories about quantum fluctuations and nothingness require a high level of abstract thinking and mathematical reasoning. These tools allow us to create models and ideas that go beyond what we can directly observe. The development of theories in cosmology and quantum mechanics relies heavily on this kind of advanced thinking, reflecting the limits of our natural understanding and the need for intellectual tools to explore the origins of the universe. Less than 100 years ago, our understanding of the universe grew in ways we never expected. This happened when astronomer Edwin Hubble discovered that the Milky Way was not the only galaxy. He showed that our galaxy, which has about 200 billion stars, is just one of many in a universe filled with countless galaxies. This discovery revealed the true size and vastness of the universe. Over the past century, we have made incredible progress in learning about space. Cosmology, the study of the universe, has become a strong field of science. Scientists have achieved amazing things, like figuring out what distant stars are made of and how galaxies move. They've also learned how stars and planets are born and how they die, and they've gained insights into the structure of space and time. Thanks to these discoveries, we now see the universe in a way our ancestors never could. The universe is a place of great forces, energy, order, and chaos. But perhaps most astonishingly, parts of this universe have become aware of themselves. We live in a universe our ancestors couldn't have imagined, and it is now clear that understanding it requires new ways of thinking, leaving behind old ideas. Our journey starts by noting that the way we talk about nature often reflects a big metaphor that shapes how we think about the universe. Throughout history, Western science has been shaped by central ideas. At one point, people saw the universe as a great mind. Later, it was thought of as a great machine. This machine metaphor has been so tightly connected with science that many people believe the two are the same. But that's not the case, and today, this view no longer helps us understand the universe as it once did. There are signs that our thinking is changing, moving towards seeing the universe more like a living organism, something that grows, evolves, and renews itself. This new way of thinking could help us better understand the universe and give us a deeper sense of our place in it. Interestingly, many people throughout history have compared the universe to an organism, both in Western traditions and other cultures. We'll explore this idea more later. However, it's important to note that we're not saying the universe is an organism. The universe is simply what it is. Whether it is more like an organism or a machine is something people will feel differently about. How we see the universe may say more about us and our place in history than about the universe itself. Still, it's clear that our understanding of the universe is improving. As we learn more, it seems we can understand the universe better by thinking of it as something alive, rather than as a machine. To explore this further, we need to look at the historical influences that shaped Western science and how they still affect our thinking today. The story we'll discuss is a brief summary, but it helps us see the difference between earlier views and the idea of the universe as something that grows and evolves. The idea that the universe is like a great mind comes from early Greek philosophers around the 4th century BCE. Many cultures saw the world as alive and full of spirit. Greek thinkers were influenced by older religious ideas, which believed that everything in nature had a soul or spirit. One of the most important Greek thinkers, Plato, created a worldview called idealism. He believed that the physical world we see is just a reflection of a higher mental reality. In this view, everything in nature had purpose and acted with intention. Later, early Christian scholars, inspired by Greek philosophy, especially Plato's ideas, believed that the universe had a higher, perfect world beyond this one. This thinking supported the Christian belief in heaven. The universe's creative force, in their view, came from outside this world, is God. During the Middle Ages, Christian teachings explained everything about life, death, and the meaning of existence. Challenging the Church's authority was dangerous and could lead to exile or worse. The focus on the afterlife made people think the world they lived in was flawed and separate from God. In the 17th century, the philosopher René Descartes had a major impact on the development of science. He introduced the idea that mind and matter are separate, creating a boundary between religion and the new scientific thinking. This allowed scientists to explore the physical world more freely while leaving the mind and spirit to religion. As scientists made new discoveries, some of these ideas began to challenge religious teachings. However, many early scientists were still deeply religious. For instance, Isaac Newton, who helped develop the idea of the universe as a machine, believed that God had set the universe in motion, but then stepped back to let it run on its own. Over time, though, the success of the machine model led many scientists and philosophers to think that reality was made entirely of matter, and the need for supernatural explanations faded. Soon, everything, including the mind, was seen as a result of physical processes. The machine metaphor became the dominant way of understanding the world, with little room for consciousness or meaning beyond biology. By the mid-19th century, Charles Darwin's ideas changed how people thought about life. Darwin and others showed that all life came from a common ancestor and had evolved over time. This new way of thinking challenged the traditional creation story. From this view, humans were seen as just another type of animal, not special in any divine way. Evolution was understood as the passing of genetic material from one generation to the next. Life seemed to follow physical laws, fitting well with the machine model of the universe. Animals, plants, and even humans were viewed as machines. Eventually, the universe itself was thought of as a machine, operating under unchanging natural laws without any purpose. Although humans seemed less important in the grand scheme of things, the machine view helped explain huge advances in medicine, anatomy, cosmology, and technology. It also gave stability to the worldview of modern, non-religious societies. The shift in how we see the universe is sometimes called the Copernican revolution. When people learned that Earth wasn't the center of the universe, it challenged both religious beliefs and the idea that human life held special importance in the cosmos. This shift pushed scientists and philosophers to promise never to assume that humans had a central or special place in the universe again. Instead, people began to find comfort in science, which gave them the ability to control nature and improve the world to meet their needs. This view was supported by the English philosopher Francis Bacon, who famously said, "Knowledge is power." Many modern thinkers believe that seeing the universe as a machine has shaped how we view the world today. While science freed people from religious control, it also made humans feel less central to the universe. As science advanced, the human mind, its goals, and its values seemed to become less important in the bigger picture. Some scholars argue that this way of thinking, without meaning or purpose, has led to feelings of separation from nature, other people, and the universe. But is seeing the universe as a machine the best way to understand reality? Is it the only way to explain the discoveries we've made? Over the past century, the machine view has been challenged by new ideas. These new ideas suggest that the universe might be better understood as something alive, like a living organism. We often think of the universe as a vast space filled with stars, planets, and galaxies. But what if the universe is more than that? Some believe that the universe might have its own kind of awareness or consciousness, and this idea has fascinated people for many years. The idea of a conscious universe isn't new. Philosophers and scientists from different times and places have asked if the universe itself could be alive in some way. Could it think or feel, even if it's on a level we don't yet fully understand? In our daily lives, we experience consciousness as something that belongs to living things. We are aware of our surroundings, we think, and we feel. But some theories suggest that consciousness might not be limited to living beings like humans and animals. These ideas propose that consciousness could be spread throughout the universe, in every star, planet, and even the space between them. This idea connects us to something much bigger. If the universe is conscious, then maybe we are all part of that consciousness. It could mean that our minds are not separate from the universe, but deeply connected to it. This changes how we think about our place in the universe. For many years, scientists have explored the universe to find answers to big questions. They study stars, galaxies, and the forces that hold everything together. But recently, some scientists and philosophers have started asking different kinds of questions. Instead of only asking how the universe works, they are asking if the universe could have a mind of its own. One of the most interesting parts of this idea is that it changes how we see ourselves. If the universe is conscious, then we are not small and insignificant. Instead, we become a part of something far bigger. Our thoughts and feelings could be part of the thoughts and feelings of the universe itself. Of course, this is just a theory. There's no solid proof that the universe is conscious, and many scientists are still trying to understand what consciousness even is. But that doesn't mean we can't think about it. Just like people long ago looked up at the stars and wondered what they were, we can look at the universe and wonder about its consciousness. There are many theories about how the universe might be conscious. Some suggest that the universe is like a living organism, with galaxies, stars, and planets working together in some way, just as our bodies are made up of tiny cells. Others believe that consciousness is something that flows through the universe, connecting everything. One theory that has gained attention is called Panpsychism. This theory suggests that consciousness isn't just limited to living things like humans or animals. Instead, consciousness might exist in everything, even in the smallest parts of the universe, like atoms and particles. If this is true, then consciousness is everywhere and in everything. When we look at the stars at night, it's easy to feel small and disconnected. But if the universe is conscious, we might actually be deeply connected to it. Just like every part of our body is connected, every part of the universe could be linked through consciousness. This gives us a new way to think about the world and our place in it. Some thinkers even suggest that consciousness might be what creates the universe. They argue that without consciousness, there would be no one to experience the universe, and so the universe might not exist in the way we understand it. In this view, consciousness and the universe are deeply connected, and one cannot exist without the other. The idea of a conscious universe also makes us rethink time. We often think of time as something that moves in one direction, past, present, and future. But if the universe is conscious, maybe time isn't as simple as we think. Some theories suggest that consciousness might exist outside of time in a way that's hard for us to imagine. This could mean the universe doesn't experience time like we do, and that consciousness could be timeless. This brings up an important question. If the universe is conscious, what does that mean for us? Are we just small parts of a larger consciousness, or do we play a bigger role? Could our thoughts and actions affect the universe, just as the universe affects us? Some believe that if the universe is conscious, then everything we do and think could have an impact, even in ways we don't fully understand. This might mean our individual consciousness is part of a much larger network, stretching across the entire universe. As we explore this idea, it's important to remember that we don't have all the answers. The conscious universe theory is still just a theory, and we may never know for sure if the universe is truly aware of itself. But thinking about it can help us feel more connected to the world and bring a sense of wonder about the universe we live in. The idea of a conscious universe also connects to spirituality for many people. Different cultures have long believed that the universe, or the earth, is alive in some way. and that everything is connected through a shared energy or spirit. In these traditions, the idea of a conscious universe isn't new, it's something that's been believed for thousands of years. As we finish this introduction to this fascinating idea, let's take a moment to reflect on the possibility that we are not alone in our consciousness. The universe, vast and mysterious, might be more alive than we ever imagined. Thinking about this can bring a sense of peace and connection as we consider that we may be part of something much bigger than ourselves. Pandora's cluster is a group of stars and galaxies that formed from at least 4 different galaxy clusters after a huge collision in the distant past. In images of this cluster, red areas show X-rays, and the blue areas show where most of the mass is located. Interestingly, the blue mass is where there's no visible light. This is what we call dark matter. In fact, about 75% of the mass in Pandora's cluster is dark matter. Scientists believe dark matter makes up about 27% of the total mass in the universe, while most of the rest is something called dark energy. The strange part is that nobody really knows what dark matter or dark energy is. So, about 95% of the universe remains a mystery, even though we've been studying it for a long time. There are big unknowns at both the smallest and largest scales in the universe. It would be amazing if all these mysteries were connected by one simple idea, but we haven't found that idea yet. It's almost like the universe is playing tricks on us. One idea that tries to explain some of these mysteries is Panpsychism, which suggests that consciousness might be a part of everything in the universe. The basic idea behind Panpsychism is simple but also controversial. Everything is conscious, from galaxy clusters to tiny particles. Even someone in a coma. It's complicated, but the cells in their body and the molecules within those cells may have some form of consciousness. What makes Panpsychism interesting is how it explains certain mysteries. Maybe dark matter and dark energy don't really exist, and we just think they do because stars and galaxies choose to act a certain way. We can sense many things like sights, sounds, and smells. Of course, small particles don't sense things like we do, but they do have properties like electric charge that interact with their surroundings. Electrons are drawn to positively charged particles and pushed away by negative ones. You could think of this attraction and repulsion as a kind of awareness. Since this attraction changes depending on distance, it suggests that electrons have a point of view. You could say the same about almost anything that has properties and interacts with other things, even theoretical objects like magnetic monopoles or the strings in string theory. One reason Panpsychism is so appealing is that it offers a way to explain some of the big mysteries of the universe. For example, we know that humans and animals are conscious, but we don't fully understand how consciousness comes to be. How do physical processes in our brain lead to awareness? Panpsychism provides an answer by suggesting that consciousness is present at a fundamental level, even in the smallest parts of the universe. In this view, consciousness doesn't just appear in complex beings like humans, it's always been there, even in the tiniest particles. This idea also challenges the traditional view that the universe is made up of 2 separate things, matter and the conscious mind. In the traditional view, these 2 things are very different, and it's hard to explain how they interact. But Panpsychism suggests that matter and mind aren't separate, they're 2 sides of the same coin. Everything in the universe has both a physical and a mental side. Now, let's step back and think about the universe as a whole. The universe is vast, with billions of galaxies, each containing billions of stars and planets. It's hard to even imagine its scale. Panpsychism asks us to consider that the entire universe might be conscious in some way. Some people may find this idea strange, but others think it offers a new way to understand the universe. If everything in the universe has some form of consciousness, then the universe itself might be seen as a kind of giant mind, with different parts experiencing different things. This doesn't mean the universe has thoughts or feelings like we do, but it suggests the universe could have a deeper, more complex nature, one that includes consciousness at all levels, from the tiniest particles to the largest galaxies. Panpsychism can also help explain some of the biggest mysteries in modern science, like dark matter and dark energy. Scientists believe dark matter makes up about 27% of the universe and dark energy makes up about 68%. Together, they account for 95% of the universe. But the strange thing is, we don't really know what dark matter or dark energy are. They don't interact with light or other things we can easily observe. Panpsychism offers a different way to think about these mysteries. What if dark matter and dark energy don't really exist as separate things, but are the result of conscious choices made by stars, galaxies, and particles? In this view, the universe might behave the way it does not because of mysterious forces, but because the parts of the universe are choosing to act in certain ways. Of course, this is just a theory, and it's not yet backed by scientific evidence. But it shows how panpsychism can offer new, creative ways of thinking about some of the biggest questions in science. One of the most interesting ideas in panpsychism is that consciousness plays a key role in the universe. In traditional science, consciousness is usually thought of as something that comes from complex brains like ours. But in panpsychism, consciousness is everywhere and is a fundamental part of reality. This raises some important questions. If consciousness is present throughout the universe, could it shape how the universe evolves? Could it influence how stars, galaxies, and planets form? Could consciousness play a role in the development of life? These are big questions, and we don't have the answers yet. But panpsychism invites us to think about the universe in a new way, one that doesn't separate mind from matter but sees them as connected. Of course, not everyone agrees with panpsychism. Some people think it's too far-fetched to believe that everything in the universe has consciousness. Critics argue that there's no solid evidence to support the idea, and it might just be wishful thinking. They believe that consciousness is something that only appears in complex beings, like humans, and doesn't exist in simple particles or objects. Others argue that even if panpsychism is true, it doesn't explain how consciousness works. Just saying that everything has consciousness doesn't tell us how consciousness arises or what it means to be conscious. These criticisms are important, but they don't take away from the fact that panpsychism offers a new and exciting way of thinking about the universe. It challenges us to rethink some of our most basic ideas and opens the door to new possibilities. The connection between quantum physics and consciousness is a fascinating topic. At the same time, the idea of the universe working like a large neural network has gained attention. Neural networks are systems of connections similar to those in our brain, where information flows and changes over time. In this view, the universe could be thought of as a massive network, where everything is connected and consciousness plays a role in this connection. One of the most interesting ideas in quantum physics is the role of the observer. In many quantum experiments, particles don't seem to settle into a specific state until they are observed. Before that, a particle exists in a state of superposition, meaning it can be in many states at once. But as soon as it's observed, the particle seems to take on one definite state. This has led some scientists and philosophers to suggest that the act of observation might play a key role in shaping reality. If observing a particle changes its behavior, then maybe consciousness, which does the observing, is somehow linked to the way the universe works at a deep level. This idea raises questions about whether consciousness could be more than just a result of brain activity. The connection between quantum physics and consciousness is still debated, but some theories suggest that consciousness might come from quantum processes happening inside the brain. One idea is that the brain might work like a quantum computer, using the strange principles of quantum physics to process information. For example, quantum particles can exist in more than one state at the same time, and they can become entangled, allowing instant communication between distant particles. Some researchers believe these quantum effects might be happening in the brain, making complex thought and possibly consciousness itself possible. While this idea is still in its early stages, it raises an interesting question. Could consciousness be linked to quantum mechanics? If the brain works using quantum principles, it might explain why consciousness is so difficult to understand with traditional scientific methods. Quantum physics could offer new insights into how our minds work and how they connect to the universe. Another idea that links quantum physics and consciousness is viewing the universe as a neural network. A neural network is a system where individual units, called neurons, connect and interact with one another. In the brain, neurons send signals to each other, allowing us to think, feel, and process information. Some scientists believe the universe might work in a similar way. Just like the neurons in our brain, the basic particles of the universe could be connected in a vast network, always interacting and sharing information. In this view, the universe could be seen as a giant brain, where everything is tied together in a web of connections. This idea is supported by quantum physics, which shows that particles can be entangled across large distances. These particles stay connected no matter how far apart they are, suggesting that the universe might be more like a network than a collection of separate objects. If the universe is a massive neural network, then consciousness could be one of the key elements in this network. Just as neurons in the brain create our awareness and thoughts, the particles of the universe might work together to create a form of universal consciousness. This would mean that consciousness isn't just something that happens inside our brains, but rather something woven into the fabric of the universe. If quantum physics and consciousness are connected, it could change how we think about both the mind and the universe. One of the biggest mysteries in science is the hard problem of consciousness and the question of how physical processes in the brain lead to the experience of being aware. Quantum physics might offer a new way to approach this problem by suggesting that consciousness is not just the result of the brain's activity, but is also something more basic to the universe itself. This brings up many questions. For example, if consciousness is tied to quantum processes, does that mean all particles in the universe have some form of awareness? Could consciousness be spread across everything, from the smallest particles to the largest galaxies? Scientists and philosophers are still exploring these questions, and we are just starting to understand what they might mean. While the idea of linking quantum physics and consciousness is gaining attention, many scientists are cautious. Critics argue that just because quantum physics is strange and hard to understand, that doesn't mean it has anything to do with consciousness. They point out that there is no clear evidence that the brain works like a quantum computer or that consciousness comes from quantum processes. In fact, most neuroscientists believe consciousness can be explained by the activity of neurons in the brain without needing quantum mechanics. According to this view, consciousness comes from electrical and chemical signals in the brain, and while we don't fully understand it yet, there's no need for quantum explanations. Imagine the universe not just as a collection of stars, planets, and space, but as something alive. This idea that the universe could be seen as a living entity has intrigued people for centuries. It suggests that the universe is not just a machine made of lifeless parts, but more like a giant organism, with everything connected and working together. When we think of life, we often think of things like plants, animals, and humans. But what if life could be something bigger, something that includes the whole universe? The idea of the universe as a living entity invites us to picture every part of the cosmos, every star, planet, and galaxy as part of a greater system that grows, changes, and evolves over time. In a living organism, all parts work together to keep it alive and functioning. Your body, for example, is made up of different systems like your heart, lungs, and brain, each playing its role. Even though these parts are different, they all work together to help you survive. The universe, in this view, could be seen in the same way. Each star, planet, and galaxy might be like a part of a larger system, playing its role in the balance of the cosmos. This doesn't mean that the universe is alive in the same way that a human or an animal is. It doesn't have a brain or thoughts. But the idea suggests that the universe behaves in ways that are similar to living things. It constantly changes, adapts, and evolves. Just like cells in a body, galaxies and stars could be seen as parts of a much larger organism that is always in motion. One reason people see the universe as alive is because of the energy that flows through it. The universe is not a still, quiet place. It's full of movement and change. Stars are born, live for billions of years, and then end in dramatic explosions. Planets form and orbit stars, while galaxies spin and sometimes even collide. This constant movement and energy make the universe seem alive, as it's always in a state of change. In this way, the universe is not just empty space, it's full of activity and energy, always growing and evolving like a living organism. Just as living things grow and change over time, so does the universe. The universe began billions of years ago with the Big Bang, which started the expansion of everything we see today. Since then, the universe has been growing, with galaxies moving farther apart as space itself stretches. This expansion is still happening, and scientists believe the universe will continue to evolve for billions of years. In a way, the universe is always being born, growing, and changing. Stars and planets are created, and over time, new ones replace the old. This cycle of birth and death is similar to what we see in living organisms. In this sense, the universe is not a still thing, it's alive with change and growth. One important idea behind seeing the universe as a living entity is that everything is connected. Just like the parts of your body work together, all the parts of the universe may be connected in ways we don't fully understand yet. This idea is supported by modern science, especially in quantum physics. We know that particles can be connected or entangled even when they are far apart. This suggests that the universe might be more interconnected than we realize. If we think of the universe as a living entity, it encourages us to see ourselves as part of something much bigger. We are not separate from the cosmos. Instead, we are deeply connected to it, just as cells are connected to the body they belong to. This view can give us a sense of belonging, reminding us that we are a small but important part of a vast living system. In this view of the universe, the Earth is not just a planet floating in space, it's part of a larger living system, with life playing a central role. The idea of Gaia from ancient mythology suggests that Earth behaves like a living organism. All the different ecosystems on Earth, like forests, oceans, and the atmosphere work together to support life. This idea can be expanded to the whole universe, with Earth playing its role in the grand system of the cosmos. From this perspective, life on Earth is not separate from the rest of the universe. Instead, it is part of the natural order of the cosmos. The Earth, with all its life, is like a cell in the larger body of the universe, playing its role in the ongoing cycle of creation and change. While the universe doesn't have a heartbeat or a mind, it acts in ways that remind us of living things. It is always in motion, growing, changing, and interacting. From the smallest particles to the largest galaxies, everything in the universe is part of a complex, connected system. This idea helps us see the universe as more than just a collection of distant stars and planets. It is an active, living system, with each part contributing to the whole. The concept of the universe as a living entity invites us to think about our place in the cosmos in a new way. It encourages us to see the bigger picture, realizing that we are part of something much larger and more connected than we often realize. Just like the cells in our bodies work together to keep us alive, we too are part of the universe's grand system of life and energy. One of the reasons people imagine the universe as a living entity is the patterns we see across different scales. For example, when we look at images of galaxies spinning in space, they sometimes reflect the patterns we see in natural systems on Earth, like the spirals of seashells or the way plants grow. These patterns suggest that the same forces shaping life on Earth might also be at work throughout the universe. At the smallest scale, cells in our body, especially nerve cells or neurons, look similar to the vast webs of galaxies that make up the universe. It's as if the universe itself has a structure, almost like a cosmic brain, where galaxies act like neurons in a much larger system. These patterns at different levels, from microscopic to cosmic, add to the idea that the universe might act like a living organism, growing and expanding according to natural laws. In living organisms, energy constantly flows to keep everything working smoothly. The same is true for the universe. Stars produce energy through nuclear fusion, which releases light and heat. This energy travels across space, affecting everything it touches. Planets like Earth absorb this energy and use it to support life. But the flow of energy doesn't stop there. When stars die, they release their materials back into the universe, which then become the building blocks for new stars, planets, and even life. This cycle of creation, death, and rebirth is much like the way energy flows through living systems. In this sense, the universe is not still, it is always moving, with energy constantly flowing and changing. Just as living things rely on energy to grow and survive, the universe depends on the flow of energy to keep evolving. Stars, planets, and galaxies all take part in this cosmic process, exchanging energy and helping to shape the structure of the universe. Another reason to think of the universe as a living entity is its ability to maintain balance. Just as the human body stays balanced through systems like the immune and nervous systems, the universe also seems to have mechanisms that keep it stable. For example, the laws of physics, such as gravity, work across the universe to maintain order. Gravity pulls objects together, helping stars form and planets stay in orbit. Even though the universe is expanding, gravity ensures that galaxies don't drift too far apart. In this way, gravity acts as a force that holds everything together, just like how living organisms have systems that keep them balanced. Additionally, the cosmic background radiation left over from the Big Bang is spread almost evenly across the universe. This radiation acts like a kind of cosmic temperature, helping to create the conditions needed for stars and galaxies to form. This balance between energy, matter, and physical laws keeps the universe working smoothly, much like the systems that keep living beings healthy and functioning. Some people believe that if the universe is alive, it might also have a form of awareness. In the same way that our brains are made up of billions of cells that work together to create consciousness, could the universe, made up of countless stars and galaxies, also have some kind of awareness? This idea doesn't mean the universe has thoughts or feelings like a person, but it suggests that consciousness might be spread throughout the universe in ways we don't yet understand. Some scientists and philosophers suggest that just as living organisms can sense and respond to their environment, the universe might also have a way of reacting to changes and keeping itself in balance. This raises the idea that consciousness is not something that only happens in the brain, but could be a fundamental part of the universe itself. If we accept the idea that the universe is a living entity, it raises interesting questions about the role of humanity. Are we just small, insignificant beings in a vast universe, or do we play a part in its larger system? In the same way that individual cells in your body each have a role to play, humans might also have a role in the bigger system of the universe. Our ability to think, learn, and explore may help the universe grow and evolve. By understanding the universe and our place in it, we become part of this larger system, helping it develop. This perspective can also encourage a greater sense of responsibility. Just as we take care of our bodies to stay healthy, we might also need to take care of the Earth and the universe around us. Have you ever looked up at the stars and wondered how everything seems so perfect for life to exist? It's almost like the universe was created just for us. But is that really true? Could it be that the universe is fine-tuned for life? In this video, we'll explore what fine-tuning means, why it matters, and whether the universe was made for humans. First, let's talk about what fine-tuning means. When scientists say the universe is fine-tuned, they mean that the basic forces and conditions in the universe seem to be just right for life to exist. These include things like the strength of gravity, the charge of electrons, and the balance between matter and energy. If any of these were even a little bit different, life, at least as we know it, might not be possible. Think of it like building a house. You need the right materials and measurements for it to stand. If the walls are too weak or the roof is the wrong size, the house will collapse. In the same way, the universe has certain conditions that allow it to support life, and those conditions seem to be just right, as if someone planned it that way. One way to explain fine-tuning is with the story of Goldilocks and the Three Bears. In the story, Goldilocks tries different bowls of porridge, chairs, and beds until she finds ones that are just right. Similarly, the universe seems to have just the right conditions for life. For example, if gravity were a bit stronger, stars might burn out too quickly. If it were weaker, stars might never form. The balance of forces in the universe allows stars to shine, planets to form, and eventually life to exist. These conditions seem so precise that it makes you wonder, why is everything so perfectly balanced? Was the universe designed for life, or is it just a coincidence? Some people believe that fine-tuning is just a coincidence. They point to the anthropic principle, which says the universe has to be this way because if it weren't, we wouldn't be here to notice it. In other words, we exist in a universe that supports life because if it didn't, we wouldn't be alive to ask the question. While this idea seems logical, it doesn't really answer the bigger question, why is the universe like this in the first place? So, was the universe made for us? This is where things get interesting. Some people believe that the fine-tuning of the universe is evidence of a higher purpose, that the universe was created by a higher power or designed to support life. This idea is known as the design argument. According to this view, the universe isn't just a random accident, but something created with intention. Others think that while the universe seems fine-tuned, it could just be a natural outcome of the laws of physics. In this view, the universe didn't have to be made for us. Instead, life adapted to the universe's conditions. Just like plants and animals adapt to their environments, life on Earth may have adapted to the universe's conditions, not the other way around. Another idea that might explain fine-tuning is the multiverse theory. This theory suggests that our universe is just one of many. In some of these universes, the conditions might be too extreme for life to exist. In others, they might be similar to ours or completely different. If there are countless universes, it's possible that we just happen to live in one where the conditions are right for life. Think of it like a lottery. The odds of winning are very low, but if millions of people are playing, someone is bound to win. The multiverse theory suggests that we're living in the universe that won the lottery by having the right conditions for life. To understand the idea of fine-tuning better, let's look at how delicate the balance of the universe really is. The forces that govern our universe, like gravity, electromagnetism, and the strong nuclear force, all need to be within a very narrow range for the universe to exist as it does. Take gravity, for example. If gravity were even slightly stronger, stars would burn out much faster. This would leave less time for planets to form, and life, as we know it, wouldn't have had a chance to develop. If gravity were slightly weaker, stars and planets might not have formed at all, and there would be no life anywhere. The fact that gravity is just right is one of the key reasons we're able to exist. Another example is the balance between matter and antimatter. After the Big Bang, equal amounts of matter and antimatter were created. If this balance were perfect, they would have destroyed each other, leaving nothing behind. But there was just a little more matter than antimatter, allowing galaxies, stars, and planets to form. This small imbalance made it possible for everything we see around us to exist. Carbon is another critical element for the fine-tuning of the universe. All known life is based on carbon, and without it, life as we know it wouldn't be possible. The way carbon forms in stars is a perfect example of fine-tuning. Inside stars, lighter elements like hydrogen and helium fuse together to form heavier elements. But for carbon to form, very precise conditions are needed. If the forces inside stars were slightly different, there wouldn't be enough carbon, and without carbon, there would be no life. While it's easy to see the universe's fine-tuning as evidence that it was made for us, another way to think about it is that life adapted to the universe. Over billions of years, life on Earth evolved to fit the conditions of our planet and the universe. Just like animals adapt to their environments, life may have simply evolved to survive in the conditions of the universe. In this view, life wasn't designed to fit the universe. Instead, the universe's conditions allowed for life to evolve. Over time, life forms developed to match the environment they found themselves in. Life evolved to fit the universe, not the other way around. Another idea is that the fine-tuning of the universe could simply be the result of chance. Some scientists think that the universe's conditions were determined randomly when it began. In this case, we just happen to live in a universe where the conditions are right for life. If the universe had different conditions, life might not exist, or life might exist in a form we can't even imagine. This opens up the possibility of life forms that don't rely on the same forces or conditions that we do. One question that comes to mind is whether the universe is fine-tuned only for humans, or if other forms of life, very different from our own, could exist somewhere else. Life as we know it depends on water, carbon, and certain chemical reactions. But what if there are other kinds of life that don't need these things? For example, scientists have considered the possibility of silicon-based life, which could exist in conditions very different from Earth's. This raises the question, could the universe support life forms that are completely different from anything we've ever seen? If so, the fine-tuning of the universe might not be just for humans or Earth-based life, but for many kinds of life we haven't yet discovered. The idea of fine-tuning has sparked philosophical and spiritual discussions. Some see fine-tuning as proof of a higher purpose or design. They believe the universe was created intentionally, with life in mind. This view suggests that there is a greater reason behind the existence of life, and the universe's conditions are part of a plan. Others take a more scientific approach. They argue that the universe's conditions happen to support life without any intentional design. This debate highlights one of the biggest questions we face, whether there's a reason behind the universe's fine-tuning or if it's just a random occurrence. No matter how you view fine-tuning, it makes us think deeply about our place in the universe. The precise conditions for life remind us how special and fragile life is. Whether the universe was made for us or we just evolved in it, the fine-tuning of the universe makes us curious about the nature of reality and our role in it. It encourages us to keep asking questions about the universe, exploring new ideas, and seeking a better understanding of the world around us. This curiosity is at the heart of science, philosophy, and spirituality. By exploring these big questions, we can gain a greater appreciation for the universe and our place in it. The question of the meaning of life is one that people have asked for thousands of years. From ancient philosophers to modern thinkers, we've all wondered at some point, why are we here? What's the purpose of it all? The search for meaning is something everyone experiences in their own way. While there may not be one single answer, asking the question is at the heart of philosophy and spirituality. In this video, we'll explore the idea of the meaning of life, how it's connected to consciousness, and why we all think about it. From the moment we become aware of ourselves, we start to wonder about life's purpose. For some, meaning comes from personal connections like family, friendships, and love. For others, it's found in achievements, helping others, or learning about the world. Some people find meaning through spirituality, believing that life is part of a greater plan or order. There's no single answer to the question of life's meaning. It's personal and can change depending on where we are in life and what we're going through. The search for meaning is a journey that evolves as we grow. Our awareness of ourselves and the world around us is at the core of our search for meaning. It's what allows us to reflect on our lives, ask big questions, and wonder why we are here. Without consciousness, we wouldn't be able to think about life's purpose at all. Consciousness lets us think beyond just our basic needs. While other animals are focused on survival, humans have the unique ability to ask why we exist. We can imagine different futures, create goals, and explore ideas that go beyond just living day to day. This ability to think deeply is why consciousness is closely tied to the search for meaning. Our awareness of life, time, and even death leads us to ask, what should we do with the time we have? Consciousness lets us reflect on the bigger picture of existence. Throughout history, different cultures and philosophies have offered various views on the meaning of life. For some, life's purpose is about finding happiness, joy, and peace in what we do. For others, it's about growth and learning, improving ourselves, and becoming better. Some spiritual traditions see life as a journey toward a higher understanding or connection with the universe. In Buddhism, for example, the meaning of life is tied to finding inner peace and understanding suffering. In Christianity, it's often seen as living in line with God's plan. Other philosophies, like existentialism, say that life doesn't come with a built-in meaning, and it's up to each person to create their own purpose. In this view, meaning isn't given to us. It's something we choose through our actions and decisions. One interesting idea is that consciousness itself might be the key to creating meaning in life. Because we are aware of ourselves and the world, we have the power to define what matters to us. Our thoughts, feelings, and experiences allow us to shape our own sense of purpose. Some people find meaning through relationships, where connection with others brings fulfillment. Others find it through work or creativity, feeling a sense of purpose when they contribute something to the world. Consciousness allows us to choose what's important to us, giving each person the freedom to create their own path in life. In this sense, the meaning of life isn't something that's given to us from the outside, it's something that comes from within. Our awareness of life's possibilities lets us decide what matters, whether that's love, knowledge, or something else unique to each person. While everyone's sense of meaning is different, there's also the question of whether there is a universal meaning to life. Is there a purpose that applies to everyone, or is it up to the individual? This question has been debated by philosophers, spiritual teachers, and thinkers for centuries. Some believe that there is a higher universal purpose behind life, one that connects all living beings and the universe. In this view, life is part of a greater whole, and each person plays a role in the big picture. For some, this idea brings comfort, knowing their life has a purpose that fits into something larger. Some people believe that the meaning of life isn't the same for everyone. They think each person has to find their own meaning, based on their own experiences, beliefs, and values. In this view, there is no single answer to the meaning of life. Instead, there are many different ways to find purpose. One reason the question of life's meaning is so powerful is because it touches on the mystery of existence. Why are we here? How did life begin? What happens when life ends? Consciousness allows us to ask these questions, but it doesn't always give us clear answers. For some, the mystery itself gives life meaning. Not having all the answers can make us feel a sense of wonder and curiosity about the universe. It pushes us to keep learning and seeking understanding. In this way, consciousness isn't just a tool for thinking about meaning, it's part of what makes life feel meaningful in the first place. A common way people find meaning is through their experiences. This can be as simple as spending time with loved ones, enjoying nature, or creating something new. The key to finding meaning through experiences is paying attention to the present moment and noticing the importance of the little things in life. For example, sharing a laugh with a friend, watching a sunset, or overcoming a personal challenge can give us a sense of fulfillment. These moments might seem small, but they can carry deep meaning because they remind us of the beauty and richness of life. Consciousness allows us to fully feel these moments, making them important parts of our life's journey. Sometimes, meaning comes from facing difficulties. Overcoming challenges, whether big or small, can give us a sense of purpose and growth. It helps us see how strong we are and can lead to a deeper appreciation of life. Another way people find meaning is through personal growth. Life is a journey where we are always learning, changing, and becoming more of who we are. Personal growth doesn't always mean achieving big goals. Sometimes it's about learning from mistakes, becoming kinder, or understanding ourselves better. When we grow as individuals, we often feel a stronger sense of purpose. Consciousness helps with this because it allows us to reflect on who we are, what we've been through, and where we want to go. By thinking about ourselves and our experiences, we can see how far we've come and set new goals for the future. Personal growth is about becoming the best version of ourselves, and this process can bring deep satisfaction and meaning. Whether it's learning a new skill, improving our relationships, or finding inner peace, personal growth adds layers of meaning to our lives. One of the most powerful ways to find meaning in life is through connection, our relationships with others, and the bonds we build. how consciousness lets us build strong connections with the people around us, whether they are family, friends, or even strangers. When we connect with others, it often gives us a sense of purpose. Helping someone, sharing our thoughts, or just being there with another person can make us feel like we belong and that our lives have meaning. These connections remind us that we're not alone in the universe. We are part of a network of relationships that bring joy, support, and understanding. Beyond relationships with people, some find a connection to the natural world. Being in nature, whether walking in the forest, swimming in the ocean, or watching animals, can remind us of the beauty and wonder of life. For many, spending time in nature brings peace and helps them feel connected to the larger world around them. Creativity is also a way that many people find meaning. Whether it's painting, writing, building, or playing music, creating something can bring fulfillment and purpose. Consciousness allows us to share our thoughts, ideas, and emotions in unique ways, and creating something helps us connect more deeply with ourselves and the world. But creativity isn't only about art. It can be found in everyday life, like solving problems, coming up with new ideas, or finding ways to help others. Consciousness lets us imagine new possibilities and make them real. In this way, creativity helps shape our world and brings meaning through the things we create, the ideas we explore, and the stories we tell. For some, creating something like a book, a song, or a piece of art feels like leaving a mark on the world. It becomes a way to contribute to life's ongoing story and leave something behind. One special thing about human consciousness is that we can think about the future. We're not just stuck in the present moment. We can imagine what's next, set goals, and work towards things we want to achieve. This ability to plan and dream gives us a sense of direction and purpose. Whether it's planning our next career move, dreaming about starting a family, or thinking of ways to make the world better, our consciousness helps us imagine what's possible and work toward it. Thinking about the future also shapes our sense of meaning because it gives us hope and purpose. Perhaps the most empowering part of the meaning of life is that we have the freedom to create our own meaning. Our consciousness gives us the ability to reflect on life and choose what matters to us. Whether it's through love, creativity, personal growth, or helping others, the meaning we find comes from our own choices and experiences. When we think about evolution, we usually picture physical changes in living things over time, such as animals adapting to their environments, plants evolving to survive in different climates, and humans developing tools to thrive. Could consciousness be not just something that comes from evolution, but also a driving force that helps shape the future of life and the universe? Consciousness, at its simplest, is the awareness that living beings have of themselves and their surroundings. For humans, it means thinking, feeling, and making decisions. But even simpler life forms, like animals and plants, show signs of awareness in the way they sense and respond to their environment. Over time, life has developed more complex forms of consciousness, starting with the basic awareness of simple organisms, leading to the self-awareness and intelligence we see in humans today. Traditionally, we think of evolution as life adapting to survive better in its environment. Consciousness, in this sense, might have evolved as a tool for survival. For example, animals that are more aware of their surroundings are more likely to avoid danger, find food, and reproduce. But consciousness doesn't just help life survive. It also allows living beings to make choices and shape their own future. For humans, consciousness has played a huge role in our evolutionary journey. Unlike other animals, humans have developed self-awareness, the ability to think about ourselves, our actions, and our future. This has allowed us to change how we interact with the world in ways no other species can. Humans have used consciousness to invent tools, build complex societies, and shape our environment. Our ability to think ahead and plan for the future has led to advancements in technology, science, and culture. Consciousness has driven us to ask big questions about the universe, come up with new ideas, and improve how we understand the world around us. In this way, consciousness has become one of the most powerful forces in human evolution, helping us not only adapt to our surroundings but also change them. As consciousness keeps evolving, it has the potential to take life beyond just survival. In the past, evolution was driven by the need to survive and reproduce, but now, consciousness has opened up new possibilities. Instead of just adapting to survive, humans can now shape the world in more intentional ways. We can make choices that go beyond basic needs, like protecting the environment, exploring space, and using technology to improve the quality of life. This ability to think beyond survival suggests that consciousness could guide the next stages of evolution. Instead of being shaped only by natural selection, life could evolve through the conscious choices of intelligent beings. As humans continue to develop technology and learn more about the universe, consciousness might play an even bigger role in shaping the future of life. One of the most exciting ways consciousness might evolve is through technology. In the last century, humans have created technologies that have dramatically changed how we live. From computers to artificial intelligence, technology is becoming more and more a part of human life, and it is shaping the future of our species. In the future, technology could help us expand our consciousness in ways we can't even imagine. Some scientists believe that as technology advances, we may one day be able to enhance human consciousness with things like brain-computer interfaces or other tools that allow us to access more information, think more clearly, or even communicate in new ways. This could be the next step in human evolution, where consciousness isn't limited to the brain's natural abilities, but is expanded through technology. In this way, consciousness could evolve alongside technology, helping us explore new possibilities and push the limits of what it means to be aware. But the evolution of consciousness may not stop with humans. As we explore the universe, it's possible that we will find other forms of life that have their own types of consciousness. These life forms might have evolved in ways that are very different from us, with levels of awareness we can't even imagine. This raises the idea that consciousness might play a role in the evolution of the universe itself. Just as life has evolved on Earth, the universe as a whole may be evolving, with consciousness playing a central role. As more intelligent life forms develop, they might help guide the future of the universe, shaping it in ways we can't yet predict. Some scientists and thinkers have even suggested that the universe could be moving toward a state of greater consciousness, where intelligent life plays a key role in shaping the future of the cosmos. Take a look at this picture of Eugene Cernan, the last astronaut from the Apollo missions to walk on the moon. There's something strange about it, do you notice it? The night sky behind him looks completely empty, with no stars in sight. In fact, in all the photos taken during the Apollo missions, you don't see any stars. Even though the universe is filled with trillions of stars, the astronauts said they couldn't see a single one from the moon. This lack of stars has led some people to believe that the moon landing was fake, but the real reason is much more interesting. The reason we don't see stars in the photos is because of the camera settings. When astronauts take pictures on the moon, they focus on the bright surface, which is lit by the sun. To capture this, the camera uses settings that block out dimmer things like stars in the background. But even when we look up from Earth at night, we see mostly darkness. So why does space look so empty? This question was first asked by German astronomer Johannes Kepler in 1610. Our galaxy, the Milky Way, has between 100 and 400 billion stars, and the universe itself has trillions of galaxies, each with trillions of stars. With so many stars, shouldn't the sky be as bright as the sun? But when we look up at night, we mostly see darkness. This confusion is known as Olbers' paradox, and it took nearly 300 years to solve. Olbers' paradox comes from the old idea that the universe has always been the same, with no beginning or end. It's called the steady-state theory, which means the universe has always existed and isn't changing. If that's true, then with all the stars out there, why is the night sky dark? One early idea was that maybe the stars were just too far away for their light to reach us. But this didn't make sense. If the universe is infinite and has always been around, even the light from the most distant stars should have reached us by now, filling the sky with their glow. Johannes Kepler had a different solution, maybe the universe isn't infinite. He suggested that stars only spread out to a certain distance, and beyond that, there's empty space. But this raised new questions. How far does the space go, and what's beyond it? Kepler's idea had problems. If the universe had an edge, the gravity from all the stars and planets could pull everything back together and cause the universe to collapse. For hundreds of years, most astronomers believed the universe was infinite, so the paradox remained unsolved. Then, in the 1800s, German astronomer Heinrich Olbers revisited the question, why is the night sky dark? People still thought the universe was unchanging at the time. Olbers suggested that the universe is full of dust and rocks that block the light from distant stars. These particles, like cosmic dust, could absorb the light and make the stars look dimmer to us. Some people still think of space this way, like clouds blocking sunlight, cosmic dust and rocks could block starlight. But Olbers' idea wasn't the full answer. Over time, the dust and rocks would heat up from the starlight and start glowing themselves, filling the sky with light again. So, this couldn't explain the darkness we see. What actually solves the mystery of the dark night sky? It took another 100 years to find the real answer. In 1929, astronomer Edwin Hubble made an important discovery. He found that galaxies were moving away from us, and the farther they were, the faster they moved. This showed that the universe wasn't staying the same or shrinking, it was expanding. This discovery led to a new question: what does an expanding universe mean? Scientists now believe the universe started from something incredibly small and dense. It then expanded very quickly in an event called the Big Bang, which happened about 13.8 billion years ago. Today, most scientists agree that the universe is about 13.8 billion years old. As we look at light that's 13.8 billion years old, we don't see stars because we're looking back to a time before stars even existed. The farther we look into space, the farther back in time we're seeing. Eventually, we reach the cosmic microwave background, which is the leftover light from the Big Bang. This isn't light from stars, but from the very early universe. The Big Bang theory explains why the universe used to be much hotter and brighter. There was a time when the whole sky would have been as bright as the sun, especially during a period called the recombination era. This means the universe's early light, known as cosmic background radiation, should have been very bright. According to Olbers' paradox, this bright light should make it hard for us to see stars in the night sky. But as the universe expanded, that light stretched out and became cooler and dimmer, making the sky dark. Since the Big Bang happened 13.8 billion years ago, the universe has followed three main rules. First, it started out tiny, hot, and dense. Second, just a fraction of a second later, it began to expand and cool down. Third, the universe keeps expanding and cooling, and astronomers believe it will eventually become so cold that all heat disappears, a state called the Big Freeze. These rules show that the universe has been getting bigger and cooler for the past 13.8 billion years. The light from the early universe has been stretched out over time, turning into longer, cooler wavelengths. This stretching of light is called the redshift effect, which is why the cosmic background radiation isn't bright today. Thanks to the redshift effect and the cosmic background radiation, we now know that the expanding universe solves Olbers' paradox. The universe started with the Big Bang and has been expanding ever since. Because the universe isn't infinitely old, there's a limit to how far we can see. The redshift also makes distant objects' light appear dimmer, which is why the night sky looks dark. The darkness of the night sky is a quiet reminder that the universe is always growing and changing. It shows us that the universe began with the Big Bang and continues to expand, solving Olbers' paradox and giving us a deeper understanding of our amazing universe. After understanding how the universe began, we also need to explore how it reached its present state. This is where cosmic inflation comes into play. Cosmic inflation refers to a very brief period right after the Big Bang when the universe expanded at an incredibly fast rate. Imagine the universe as a tiny, tightly packed point that suddenly stretched out, growing at an unimaginable speed. This expansion happened in less than a fraction of a second, making the universe much larger almost instantly. Scientists believe that this rapid expansion was powered by a unique type of energy that existed in the early universe, often called inflationary energy. This energy caused space to stretch faster than the speed of light. It's like blowing up a balloon rapidly, causing it to expand from the size of a pinhead to the size of a basketball in an instant. Before inflation, the universe was chaotic, with random fluctuations in density and temperature. However, inflation spreads everything out evenly, making the universe smooth and uniform on a large scale. Even though inflation smoothed out the universe, it also left behind tiny irregularities or fluctuations. These small differences in density were amplified by gravity over time, forming the galaxies, stars, and planets we see today. One of the key pieces of evidence for inflation is the cosmic microwave background radiation. The CMB is the faint afterglow from the Big Bang, and it gives us a snapshot of the universe when it was only 380,000 years old. The uniformity of the CMB, with slight temperature fluctuations, perfectly matches the predictions made by the theory of inflation. The way galaxies and galaxy clusters are distributed throughout the universe also supports the idea of inflation. The size and spread of these structures align with the tiny fluctuations left behind by inflation. Additionally, the universe appears to be geometrically flat, meaning it follows the rules of Euclidean geometry. And inflation explains why the universe is flat, because the rapid expansion smoothed out any curvature. Inflation also solves the horizon problem, which questions why distant parts of the universe, so far apart, have the same temperature and properties. During inflation, regions that were once close together were spread out across the universe, explaining their similar conditions. Inflation is driven by a hypothetical field called the inflaton field. This field, tied to a particle called the inflaton, had very high energy density which powered the rapid expansion. As the universe expanded, the inflaton field's energy decreased, ending the inflationary period. Once inflation ended, the energy from the inflaton field was converted into particles and radiation, heating up the universe and triggering the next phase called the Big Bang nucleosynthesis, where the first elements, like hydrogen and helium, were formed. During inflation, tiny quantum fluctuations in the inflaton field were stretched to large scales. These small fluctuations became the seeds for over- and underdensities in the early universe. Over time, these tiny differences were amplified by gravity, eventually forming large structures like galaxies and galaxy clusters. Cosmic inflation helps explain several key features of the universe: why the universe looks the same in all directions, why the CMB is so uniform, why the universe has a flat geometry, and how galaxies and large-scale structures emerged from small fluctuations in the early universe. Chaotic inflation theory expands on the concept of inflation by explaining how the early universe may have experienced a period of extremely rapid, uneven expansion. To understand chaotic inflation, imagine a magic balloon. It starts off tiny, nearly invisible, and then suddenly inflates at an extraordinary speed, much faster than any normal balloon. But as it expands, some parts grow rapidly while others remain unchanged. This is similar to what chaotic inflation suggests about the early universe. Some regions of space expanded quickly, while others did not, creating a patchy, uneven universe. In this theory, the universe didn't require a perfectly smooth or uniform starting point for its rapid expansion. Instead, the universe could have expanded from nearly any initial condition, whether it was smooth, bumpy, or anything in between. This variation in expansion rates across different regions is caused by a special energy field called the inflaton field. The inflaton field is like a landscape of hills and valleys. Regions of space sitting on top of high hills in this landscape expand rapidly due to the field's high energy. Other regions in the valleys, where the energy is lower, expand more slowly or not at all. Over time, the rapidly expanding areas dominate, leading to a universe that grows unevenly, with faster expanding regions taking over. Chaotic inflation complements the standard Big Bang theory by providing a mechanism for how different regions of the universe expanded at different rates. It also suggests that this expansion could have occurred under many different conditions, not requiring a perfectly smooth start. This patchy expansion might explain the large-scale structure of the universe today, where galaxies and clusters are spread out in complex patterns. Chaotic inflation also introduces the possibility of a multiverse, a collection of universes where different regions of space have expanded differently and may even have different physical laws. In chaotic inflation, the universe doesn't have a fixed edge or boundary. Instead, it's made up of regions that expanded at varying rates, some of which have stretched so far that they now lie beyond our observable reach. The true edge of the universe is always changing as it continues to expand. This theory supports the idea of a multiverse where different universes, with their own unique properties, might exist beyond what we can observe. Instead of a single defined boundary, the universe becomes a dynamic and ever-expanding frontier full of possibilities. Understanding the shape of the universe is key to answering questions about its boundaries and whether it has an edge. For centuries, people thought the universe was shaped like a sphere, with Earth at the center, separated from the rest by a boundary where space ends. This idea, going back to Aristotle, assumed that beyond this boundary there was simply nothing. However, this concept posed complex questions about what happens at the boundary. As scientists examined the universe more deeply, it became clear that we don't see any evidence of such a boundary. In fact, light seems to travel freely, except near black holes where it gets trapped. So, instead of a universe with a physical edge, it's more like we're on the surface of a sphere. Consider Earth. You can travel around it endlessly without hitting an edge because gravity brings you back to your starting point. Similarly, the universe might curve in a way that allows you to travel forever without ever encountering a boundary. This concept is tied to the idea of curved space. There are three potential shapes for the universe: positively curved, negatively curved, or flat. A positively curved universe is like the surface of a sphere, finite but without an edge. A negatively curved universe is more like a saddle where space curves outward. Finally, a flat universe behaves like an endless sheet of paper where space doesn't curve in any direction. The concept of critical density explains what kind of universe we might live in. If the universe's density is balanced perfectly between positive and negative curvature, it's called a flat universe. In this scenario, the density of the universe, called omega, is exactly 1, meaning the effects of gravity and dark energy are balanced. A flat universe is infinite, with space stretching out in all directions without ever closing in on itself. But how do we determine the shape of the universe? There are two primary ways to measure this. One involves adding up the total energy densities of the universe by observing its large-scale properties. The uniformity of the cosmic microwave background, the faint afterglow of the Big Bang, suggested that the universe might be near critical density. The discovery of cosmic acceleration in the late 1990s showed that space might be either slightly negatively curved or very close to flat. The second method is more precise and involves studying the CMB. The CMB acts as a snapshot of the universe when it was only 379,000 years old. By measuring the distances between small fluctuations in the temperature of the CMB, scientists can determine the curvature of space. In a positively curved universe, the angles between distant points in the CMB would add up to more than 180 degrees. In a negatively curved universe, the angles would add up to less than 180 degrees. In a flat universe, the angles would add up to exactly 180 degrees. So far, studies of the CMB, including data from NASA's Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, suggest that the universe is remarkably flat, with any curvature being so slight that it's nearly impossible to detect. However, this creates a new puzzle known as the flatness problem. If the universe is so perfectly flat, why is that? Scientists believe that this perfect balance likely stems from the early moments of the universe during a phase called cosmic inflation, when the universe expanded incredibly rapidly. Inflation would have smoothed out any curvature, leaving the universe nearly flat today. The shape of the universe remains one of the greatest mysteries in cosmology. It might be flat and infinite, curved, but on such a large scale that we can't measure it, or it could have a hidden shape that we don't yet understand. While current evidence points toward a flat universe, the true shape could be more complex than we can imagine, and solving this mystery remains a key goal in our exploration of the cosmos. Is there a center of the universe? This is a question that has fascinated people for centuries. From our viewpoint, it can seem like Earth is at the middle of everything, but modern science shows that the reality is much more complex. To understand whether the universe has a center, we need to delve into the history of its expansion and how it all began. In the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. He found that galaxies are not only far away from us, but that, on average, they are all moving away from each other. This was a huge shift from the previous belief that the universe was static and unchanging. Hubble's observations aligned with Einstein's theory of general relativity, which suggested that the universe must be either expanding or contracting. This led to the understanding that our universe is expanding, and it has been ever since its beginning. According to this view, long ago, everything in the universe was compressed into an incredibly tiny, dense point known as the singularity, the starting point of the Big Bang. So, where is the Big Bang? If everything started from a singular point, wouldn't that be the center of the universe? Surprisingly, no. The concept of a center doesn't really apply to the universe the way it does to more familiar objects, like a ball or a planet. The Big Bang didn't happen at a single location in space. Instead, it happened everywhere in space at the same time. Imagine the universe as a balloon. As you blow it up, every point on the surface of the balloon moves away from every other point, but there is no central point on the surface. Similarly, the universe is expanding in all directions, but it doesn't have a single central point from which the expansion started. This might be hard to picture because we're used to thinking of objects having centers and edges. However, in the context of the universe, there is no center and no edge. The expansion is happening uniformly throughout all space. If we imagine the universe as infinite, it becomes impossible to define a central point. Even if the universe is finite, it could curve back on itself at large scales, much like the surface of a sphere. In this case, there still wouldn't be a center in the traditional sense. Space would curve around without ever ending, meaning you could travel in a straight line and eventually return to your starting point, just as you could if you traveled around the Earth. In conclusion, while it may feel like there should be a center of the universe, the truth is that there isn't one. The Big Bang happened everywhere at once, and the universe continues to expand uniformly. Whether the universe is infinite or finite, it doesn't have a traditional center or edge, making the idea of a central point irrelevant in the grand structure of the cosmos. Think of it like this. On Earth, we can point to the center of the Earth's three-dimensional space, the molten core, but we can't point to the center of the Earth's surface. Any point on the surface could be considered the center because no one spot is more central than another. The same is true for the universe. The Big Bang wasn't an explosion that happened at a single point in space. Instead, it was a moment in time that happened everywhere in the universe all at once. It happened in the room you're sitting in right now, and it also happened in the most distant galaxy we can see. Every part of the universe, including the vast stretches we cannot see, was part of this event. Here's the twist. The universe is about 13.77 billion years old. Because light travels at a limited speed, we can only see part of the universe. The farthest light we can observe comes from objects around 45 billion light-years away, thanks to the fact that space itself is expanding faster than light. This creates a horizon beyond which the rest of the universe is hidden from us, like standing in a dark forest with a flashlight. You can only see what the beam reaches. Because we observe all other galaxies moving away from us, it might feel like we're at the center of the universe. But this is a trick of perspective. Every galaxy, including those we observe from here on Earth, sees the same thing: galaxies moving away from them. The truth is, there's no one central point in the universe. This is simply how an expanding universe behaves. To understand why, imagine blowing up a balloon. As the balloon inflates, every point on the surface moves away from every other point. None of these points is the center of the expansion. Everything is moving apart equally. Similarly, the universe is expanding everywhere at once, not from a single spot. The Big Bang wasn't an explosion from one place into empty space. It was space itself expanding and stretching, happening everywhere at the same time. Now let's talk about the observable universe. Because light has a finite speed, we can only observe the parts of the universe from which light has had enough time to reach us. This creates a sort of spherical boundary around us called the observable universe, which has a radius of about 45 billion light-years. This doesn't mean the universe is only 45 billion light-years wide. It's just the limit of what we can see. Beyond that, the universe keeps going, but it remains hidden from us due to the limits of light speed and the constant expansion of space. Think about standing in a foggy field. You can only see as far as the fog allows, but you know the field extends beyond that. The edge of your vision isn't the edge of the field, it's just the limit of what you can observe. In the same way, the observable universe is just the part we can see, but the true size of the universe is much larger and might even be infinite. This uniform expansion means that, from any point in the universe, it looks like you're at the center. If you were in a galaxy billions of light years away, you would see other galaxies moving away from you, just like we do from Earth. This expansion makes every point seem like the center of the universe, but in reality, no single point holds that title. Because space is expanding evenly, there's no central location to the universe, and there's no physical edge we can reach. So, does this mean that the expanding universe will forever hide its true limits from us? Let's explore that idea further. Back in the 4th century BCE, a Greek scholar named Archytas imagined reaching the edge of the universe and trying to extend his hand further. He believed that if there was nothing beyond, then the universe must be infinite. In the 16th century, Italian philosopher Giordano Bruno also thought the universe was infinite, filled with countless stars and planets. In the 17th century, philosopher Thomas Hobbes took a more practical view. He believed that speculating about an infinite universe wasn't useful since we couldn't measure or observe it. He suggested focusing on what could be understood. This approach has shaped modern science, but despite the caution, some cosmologists still explore the question of the universe's infinity using today's technology and centuries of accumulated knowledge. When we look into space, it's like standing on an island, seeing only as far as the horizon. Light travels at a constant speed, so looking far into space is like looking back in time. We can observe galaxies as they existed 1 billion, 5 billion, or even 10 billion years ago. The farthest galaxies we can see emitted their light 13.8 billion years ago, but due to the universe's expansion, these galaxies are now about 46 billion light-years away. Even though we've peered deep into space, there's no evidence of a boundary. On the largest scales, the universe appears uniform, with no regions hotter or colder, or more crowded with galaxies than others. This uniformity suggests the universe is even larger than we can observe. While our technology has its limits, our imagination doesn't. It's natural to wonder what lies beyond the observable universe, even if such speculation doesn't give us clear answers. Just like a person sailing the ocean without encountering an edge because Earth is round, the universe might be similarly curved, finite, but without a boundary. Cosmologists test this idea by understanding geometry. On a flat surface, parallel lines stay parallel forever, while on a sphere, they eventually meet. Edwin Hubble tried to use this logic in the 1930s by counting galaxies to determine the universe's shape. Today, Astronomers use tools like the Wilkinson Microwave Anisotropy Probe to measure the universe's mass and energy, helping us understand whether the universe is flat, positively curved, or negatively curved. Scientists also examine the cosmic microwave background, the afterglow of the Big Bang, for signs of curvature. If space is curved, it would help us understand whether the universe is finite but without edges. The instruments scientists use, though powerful, have limits, making it challenging to determine the universe's true shape. So far, our observations suggest the universe appears flat, but this could simply be because we're not able to see its full shape. The flatness we observe sets a minimum size for the universe beyond what we can see, at least 37 trillion light-years in diameter. This is thousands of times larger than the observable universe, and that's just the smallest possible size. The universe could be much larger or even infinite. The idea of an infinite universe is hard to grasp, but as we continue to explore and learn, we may get closer to answering whether the universe truly has no limits. In 1980, Benoit Mandelbrot was one of the first to use computer graphics to visualize concepts that couldn't easily be drawn by hand. He introduced a new type of geometry, which he called fractal, from the Latin word for broken or shattered. Fractals are structures that look similar no matter how much you zoom in or out, always revealing more detail without ever becoming simpler. This creates endless complexity. Mandelbrot used computers to create the now famous Mandelbrot set, demonstrating the idea of fractals. He also noticed that similar patterns are found in nature, like in fern leaves, Romanesco broccoli, and even in the clustering of galaxies. He wondered if the entire universe could be a fractal. While the universe appears mostly uniform at the largest scales we can observe, the idea of fractal-like patterns beyond our observational limits remains intriguing. As we explore the cosmos, we encounter infinity at every turn. The universe is expanding, with galaxies moving away from each other, much like a loaf of bread rising in the oven. If the universe started from an infinite point, then our observable universe was just a small part of that infinite expanse. Over time, although the observable universe grows, it's really just a measure of how far light has traveled. This leads to the idea that while the physical universe is getting less dense as it expands, the observable universe is only a fraction of the whole. Galaxies beyond our local group are moving away. Looking into the future, if no new forces interfere, the universe will continue expanding. Galaxies will drift farther apart, stars will move away from each other, and eventually, the universe will enter a state called the heat death. This isn't a single event, but rather a gradual fading into cold darkness. The observable universe will keep expanding, and while it may become infinitely large, we'll only ever be able to explore a finite part of it due to the limits imposed by the speed of light and the expansion of space itself. Looking back in time, we see the universe contracting, becoming smaller, denser, and hotter. Eventually, it shrinks to a point where our understanding of physics breaks down. We know that beyond a certain point smaller than a Planck length, our physical models no longer work. The universe may have started expanding from an infinitely small, dense, and hot point, but we have no way to understand what that might have looked like. Cosmologists like Alan Guth and Andre Linde have suggested that what we observe might just be a small inflating region within an infinitely large universe. This idea, known as eternal inflation, suggests that our universe is one of countless bubble universes that form in an endless cosmic expanse. Each of these bubbles might operate under different physical laws, potentially leading to a multiverse, a collection of infinite universes. In this multiverse, each universe could have different physical constants, like gravity or particle mass, creating limitless possibilities. Our Big Bang might just be a small event in an infinite cosmic history, and the heat death of our universe might just be a detail within a much larger framework. Roger Penrose's idea of conformal cyclic cosmology suggests that when our universe becomes infinitely large and enters its heat death, it might actually mark the beginning of a new universe. In this view, the cycles of the universe repeat in a continuous loop, where the end of one universe gives rise to another. Beyond infinity lies the concept of endless possibilities. Whether through fractals, a multiverse, or an ever-repeating cosmic cycle, the universe challenges our understanding of space, time, and existence itself. According to various theories, our universe might be just one bubble in a vast cosmic sea where countless other universes exist, each with its own unique physical laws. British physicist Brian Cox has discussed how the concept of multiple universes fits within the framework of eternal inflation, a theory that builds on the Big Bang. In this theory, the universe we observe is just one of many bubbles in a frothy sea of spacetime. These bubble universes are continuously being formed. The process starts when a region of space stops its rapid inflation. However, not all parts of spacetime cease inflating at the same time. While one part of space cools down and forms a universe like ours, other regions continue expanding, leading to the constant creation of new bubble universes. Each of these universes might have its own set of physical laws, potentially very different from what we experience in our universe. To better understand the multiverse, imagine an immense library filled with an infinite number of books. Each book represents a different universe. In this infinite library, every possible combination of physical laws and outcomes exists somewhere. In one book, gravity could be slightly weaker, leading to taller creatures and grander buildings. In another, the speed of light could be slower, profoundly changing how energy moves in that universe. The differences between these universes go beyond just physical laws. Entirely different courses of history and evolution could unfold. For example, imagine a universe where the dinosaurs never went extinct, evolving into intelligent beings. Or consider a universe where matter is composed of entirely different elements, leading to stars and planets formed from dark matter instead of the substances we know. Each bubble universe might represent a different story in this cosmic library, and the possibilities are truly limitless. The multiverse theory challenges us to think beyond our own universe, exploring the idea that there are infinite variations of reality, each with its own unique laws, histories, and possibilities. Is there any evidence that our universe is part of a multiverse? Could we be one bubble in a cosmic sea of universes? In the book Endless Universe, Beyond the Big Bang, authors Paul Steinhardt and Neil Turok propose a radical idea. They suggest that the universe didn't start with a single Big Bang, but instead goes through endless cycles of cosmic events. This theory includes the possibility that our universe has collided with other bubble universes in the multiverse. In 2015, researcher Ranga Ramchari found unusual signals while studying the cosmic microwave background, which is the oldest detectable light in the universe. He proposed that these signals might indicate a collision between our universe and another. Although it's unclear whether this interaction was minor or significant, Cherry's work adds weight to the idea that our universe might be just one in a vast multiverse. The CMB is often called the afterglow of the Big Bang. It's like a snapshot of the universe's infancy, offering a glimpse of how the universe has expanded and evolved. When astronomers study the CMB, they see not only a uniform glow, but also a complex pattern of light and dark patches. These patches show tiny temperature differences that helped shape the large-scale structure of the universe. One mysterious feature in the CMB is known as the cold spot, an area of unusually low temperatures. One theory about this cold spot is that it might be a cosmic bruise, evidence that our universe came into contact with another universe. This idea suggests that such collisions between universes could leave detectable marks, offering potential evidence of a multiverse. In 2007, theoretical physicist Laura Massini-Houghton proposed a hypothesis about the cold spot. She suggested that it could be the result of our universe interacting with another universe. According to her theory, if multiple universes exist, they might occasionally collide, leaving behind detectable bruises in the form of anomalies like the cold spot. The gravitational pull from a nearby universe might have slowed down the expansion of our universe in that specific region, causing the cooler temperatures we see today. This idea aligns with Rangaram-Cherry's 2015 findings, which also suggested that features in the CMB might be signs of a past collision with another universe. Both Massini-Houghton and Cherry believe that these interactions between universes could cause fluctuations in cosmic inflation, leaving scars or dents in the fabric of our universe. These hypotheses raise important questions about the history of our universe. One of the key ideas of inflation theory is that everything in the universe should be evenly distributed. However, the cold spot and other anomalies challenge this assumption, suggesting a more complex history where our universe may have interacted with others.